to the Sysadmin's nap room. Tonight, we're reading through a request for comments document. This is technical documentation that defines Internet protocols and standards used across networks worldwide. No commentary, no explanations. Just the steady, monotone reading of specification text, designed to help you disconnect from the day and drift into sleep. Let the familiar rhythm of technical language wash over you. You don't need to understand it. You don't need to remember it. Just listen, relax, and let go. The manual begins now. The Hypertext Transfer Protocol, HTTP, is an application-level protocol for distributed, collaborative, hypermedia information systems. HTTP has been in use by the Worldwide Web Global Information Initiative since 1990. The first version of HTTP, referred to as HTTP/0.9, was a simple protocol for raw data transfer across the Internet. HTTP/1, as defined by RFC 1945-6, improved the protocol by allowing messages to be in the format of MIME-like messages, containing meta-information about the data transferred and modifiers on the request/response semantics. However, HTTP/1 does not sufficiently take into consideration the effects of hierarchical proxies, caching, the need for persistent connections, or virtual hosts. In addition, the proliferation of incompletely implemented applications calling themselves HTTP/1 has necessitated a protocol version change in order for two communicating applications to determine each other's true capabilities. This specification defines the protocol referred to as HTTP/1.1. This protocol includes more stringent requirements than HTTP/1 in order to ensure reliable implementation of its features. Practical information systems require more functionality than simple retrieval, including search, front-end update, and annotation. HTTP allows an open-ended set of methods and headers that indicate the purpose of a request. 47. It builds on the discipline of reference provided by the Uniform Resource Identifier, URI-3, as a location, URL-4, or name, earn 20, for indicating the resource to which a method is to be applied. Messages are passed in a format similar to that used by Internet Mail 9, as defined by the multi-purpose Internet Mail extensions MIME 7. HTTP is also used as a generic protocol for communication between user agents and proxies/gateways to other Internet systems, including those supported by the SMTP 16, NNTP 13, FTP 18, Gopher 2, and WAIS 10 protocols. In this way, HTTP allows basic hypermedia access to resources available from diverse applications. The keywords must not, required, shall not, SHOULD, should not, recommended, may, and optional in this document are to be interpreted as described in RFC 2119-34. An implementation is not compliant if it fails to satisfy one or more of the must or required level requirements for the protocols it implements. An implementation that satisfies all the must or required level requirements for its protocols is said to be unconditionally compliant. One that satisfies all the must level requirements, but not all the should level requirements for its protocols, is said to be conditionally compliant. This specification uses a number of terms to refer to the roles played by participants in and objects of the HTTP communication connection, a transport layer virtual circuit established between two programs for the purpose of communication. Message, the basic unit of HTTP communication, consisting of a structured sequence of octets matching the syntax defined in section 4 and transmitted via the connection request an HTTP request message as defined in section 5. Response, an HTTP response message as defined in section 6. Resource, a network data object or service that can be identified by a URI as defined in section 3.2. Resources may be available in multiple representations, e.g., multiple languages, data formats, size, and resolutions, or vary in other ways. Entity, the information transferred as the payload of a request or response. An entity consists of meta information in the form of entity header fields and content in the form of an entity body, as described in section 7. Representation, an entity included with a response that is subject to content negotiation, as described In Section 12, there may exist multiple representations associated with a particular response status. Content negotiation. The mechanism for selecting the appropriate representation when servicing a request as described in Section 12. The representation of entities in any response can be negotiated, including error responses. Variant. A resource may have one or more than one representation associated with it at any given instant. Each of these representations is termed a variant. Use of the term does not necessarily imply that the resource is subject to content negotiation. Client. A program that establishes connections for the purpose of sending requests. User agent. The client which initiates a request. These are often browsers, editors, spiders, web traversing robots, or other end user tools. Server. An application program that accepts connections in order to service requests. By sending back responses, any given program may be capable of being both a client and a server. Our use of these terms refers only to the role being performed by the program for a particular connection, rather than to the program's capabilities. In general, likewise, any server may act as an origin server proxy gateway or tunnel switching behavior based on the nature of each request. Origin server. The server on which a given resource resides or is to be created. Proxy. An intermediary program which acts as both a server and a client for the purpose of making requests on behalf of other clients' requests are serviced internally or by passing them on with possible translation to other servers. A proxy must implement both the client and server requirements of this specification. A transparent proxy is a proxy that does not modify the request or response beyond what is required for proxy authentication and identification. A non-transparent proxy is a proxy that modifies the request or response in order to provide some added service to the user agent, such as group annotation. Services media type transformation, protocol reduction, or anonymity filtering, except where either transparent or non-transparent behavior is explicitly stated. The HTTP proxy requirements apply to both types of proxies. Gateway. a server which acts as an intermediary for some other server. Unlike a proxy, a gateway receives requests as if it were the origin server for the requested resource. The requesting client may not be aware that it is communicating with a gateway. Tunnel, an intermediary program which is acting as a blind relay between two connections. Once active, a tunnel is not considered a party to the HTTP communication, though the tunnel may have been initiated by an HTTP request. The tunnel ceases to exist when both ends of the relayed connections are closed. Cache, a program's local store of response messages, and the subsystem that controls its message storage retrieval and deletion. A cache stores cacheable responses in order to reduce the response time and network bandwidth consumption on future equivalent requests. Any client or server may include a cache, though a cache cannot be used by a server that is acting as a tunnel. Cacheable. A response is cacheable if a cache is allowed to store a copy of the response message for use in answering subsequent requests. The rules for determining the cacheability of HTTP responses are defined in Section 13. Even if a resource is cacheable, there may be additional constraints on whether a cache can use the cached copy for a particular request. First-hand. A response is first-hand if it comes directly and without unnecessary delay from the origin server, perhaps via one or more proxies. A response is also first-hand if its validity has just been checked directly with the origin server. Explicit expiration time. The time at which the origin server intends that an entity should no longer be returned by a cache without further validation. Heuristic expiration time. An expiration time assigned by a cache when no explicit expiration time is available. Age. The age of a response is the time since it was sent by or successfully validated with the origin server. Freshness. Lifetime. The length of time between the generation of a response and its expiration time. Fresh. A response is fresh if its age has not yet exceeded its freshness lifetime. Stale. A response is stale if its age has passed its freshness lifetime. Semantically transparent. A cache behaves in a semantically transparent manner respect to a particular response, when its use affects neither the requesting client nor the origin server, except to improve performance when a cache is semantically transparent. The client receives exactly the same response, except for hop-by-hop headers, that it would have received had its request been handled directly by the origin server, validator, a protocol element, e.g., an entity tag, or a last modified time, that is used to find out whether a cache entry is an equivalent copy of an entity upstream / downstream, upstream and downstream. Describe the flow of a message. All messages flow from upstream to downstream. Inbound / outbound, inbound and outbound refer to the request and response paths for messages. Inbound means traveling toward the origin server, and outbound means traveling toward the user agent. 1.4 Overall operation. The HTTP protocol is a request/response protocol. A client sends a request to the server in the form of a request method, URI, and protocol version, followed by a MIME-like message containing request modifiers, client information, and possible body content over a connection with a server. The server responds with a status line, including the message's protocol version, and a success or error code, followed by a MIME-like message containing server information, entity meta-information, and possible entity body content. The relationship between HTTP and MIME is described in Appendix 19.4. Most HTTP communication is initiated by a user agent and consists of a request to be applied to a resource on some origin server. In the simplest case, this may be accomplished via a single connection, V, between the user agent, UA, and the origin server, O. Request chain UAVO. Response chain. A more complicated situation occurs when one or more intermediaries are present in the request/response chain. There are three common forms of intermediary: proxy, gateway, and tunnel. A proxy is a forwarding agent receiving requests for a URI in its absolute form, rewriting all or part of the message, and forwarding the reformatted request toward the server identified by the URI. A gateway is a receiving agent acting as a layer above some other servers, and if necessary, translating the requests to the underlying server's protocol. A tunnel acts as a relay point between two connections without changing the messages. Tunnels are used when the communication needs to pass through an intermediary, such as a firewall. Even when the intermediary cannot understand the contents of the messages, request chain UAV a VBVCVO. Response chain. The figure above shows three intermediaries, A, B, and C, between the user agent and origin server. A request or response message that travels the whole chain will pass through four separate connections. This distinction is important because some HTTP communication options may apply only to the connection with the nearest non-tunnel neighbor, only to the endpoints of the chain, or to all connections along the chain. Although the diagram is linear, each participant may be engaged in multiple simultaneous communications. For example, B may be receiving requests from many clients other than A, and slash or forwarding requests to servers other than C at the same time that it is handling A's request. Any party to the communication which is not acting as a tunnel may employ an internal cache for handling requests. The effect of a cache is that the request/response chain is shortened if one of the participants along the chain has a cached response applicable to that request. The following illustrates the resulting chain. If B has a cached copy of an earlier response from O via C for a request which has not been cached by UA, or A request, chain UAV a VB. C. O response, chain. Not all responses are usefully cacheable, and some requests may contain modifiers which place special requirements on cache behavior. HTTP requirements for cache behavior and cacheable responses are defined in Section 13. In fact, there are a wide variety of architectures and configurations of caches and proxies currently being experimented with or deployed across the World Wide Web. These systems include national hierarchies of proxy caches to save transoceanic bandwidth, systems that broadcast or multicast cache entries, organizations that distribute subsets of cached data via CD-ROM, and so on. HTTP systems are used in corporate intranets over high bandwidth links and for access via PDAs with low power radio links and intermittent connectivity. The goal of HTTP/1.1 is to support the wide diversity of configurations already deployed, while introducing protocol constructs that meet the needs of those who build web applications that require high reliability, and failing that, at least reliable indications of failure. HTTP communication usually takes place over TCP/IP connections. The default port is TCP 8019, but other ports can be used. This does not preclude HTTP from being implemented on top of any other protocol on the internet or on other networks. HTTP only presumes a reliable transport. Any protocol that provides such guarantees can be used. The mapping of the HTTP/1.1 request and response structures onto the transport data units of the protocol in question is outside the scope of this specification. In HTTP/1, most implementations used a new connection for each request/response exchange. In HTTP/1.1, a connection may be used for one or more request/response exchanges, although connections may be closed for a variety of reasons. See section 8.1. 2. Notational conventions and generic grammar. 2.1. Augmented BNF. All of the mechanisms specified in this document are described in both prose and an augmented Backus-Naur form, BNF, similar to that used by RFC 822. 9. Implementors will need to be familiar with the notation in order to understand this specification. The augmented BNF includes the following constructs. Name equals definition. The name of a rule is simply the name itself, without any enclosing, and is separated from its definition by the equals character. White space is only significant in that indentation of continuation lines is used to indicate a rule definition that spans more than one line. Certain basic rules are in uppercase, such as SB, LWS, HT, CRLF, digit, alpha, etc. Angle brackets are used within definitions whenever their presence will facilitate discerning the use of rule names. Literal quotation marks surround literal text. Unless stated otherwise, the text is case-insensitive. Rule-on-rule-to elements separated by a bar are alternatives, e.g., yes, no will accept yes or no. Elim, foo bar, elim, elements enclosed in parentheses are treated as a single element. Thus, elim foo bar elim allows the token sequences elim foo elim and elim bar elim preceding an element indicates repetition. The full form is NM element, indicating at least N, and at most M occurrences of element. Default values are 0 and infinity, so that element allows any number, including 0. One element requires at least 1, and 1-2 element allows 1 or 2. Rule square brackets enclose optional elements. Foo bar is equivalent to 1 foo bar. N rule specific repetition. N element is equivalent to N element, that is, exactly N occurrences of element. Thus 2-digit is a 2-digit number, and 3 alpha is a string of 3 alphabetic characters. Number rule a construct number is defined, similar to for defining lists of elements. The full form is N number M element, indicating at least N, and at most M elements, each separated by 1 or more commas, and optional linear white space, LWS. This makes the usual form of lists very easy. A rule such as LWS element, LWS element can be shown as one number element wherever this construct is used. Null elements are allowed, but do not contribute to the count of elements present. That is, element is permitted, but counts as only 2 elements. Therefore, where at least 1 element is required, at least 1 non-null element must be present. Default values are 0 and infinity, so that number element allows any number, including 0. One number element requires at least 1, and one number 2 element allows 1 or 2. Comment a semicolon. Set off some distance to the right of rule text. Starts a comment that continues to the end of line. This is a simple way of including useful notes in parallel with the specifications. Implied LWS, the grammar described by this specification, is word-based, except where noted otherwise. Linear white space, LWS, can be included between any 2 adjacent words, token or quoted string, and between adjacent words and separators, without changing the interpretation of a field. At least 1 delimiter LWS and slash or separators must exist between any 2 tokens for the definition of token below, since they would otherwise be interpreted as a single token. 2.2 Basic rules. The following rules are used throughout this specification to describe basic parsing constructs. The US ASCII coded character set is defined by ANSI x3.4 1986. 21. Octet equals any 8-bit sequence of data char equals any US ASCII character. Octets 0. 127. UPALPHA equals any US ASCII uppercase letter A. C. LOALPHA equals any US ASCII lowercase letter A. C. Alpha equals UPALPHA LOALPHA digit equals any US ASCII digit 0. 9. CTL equals any US ASCII control character. Octets 0, 31. And Del 127. CR equals US ASCII CR carriage return 13. LF equals US ASCII LF line feed 10. SB equals US ASCII SB space 32. HT equals US ASCII HT horizontal tab 9 equals US ASCII double quote mark 34. HTTP/1.1 defines the sequence CRLF as the end-of-line marker for all protocol elements except the entity body. See Appendix 19.3 for tolerant applications. The end-of-line marker within an entity body is defined by its associated media type, as described in Section 3.7. CRLF equals CRLF HTTP/1.1 header field values can be folded onto multiple lines if the continuation line begins with a space or horizontal tab. All linear white space, including folding, has the same semantics as SB. A recipient may replace any linear white space with a single SB before interpreting the field value or forwarding the message downstream. LWS equals CRLF1 SBHT. The text rule is only used for descriptive field contents and values that are not intended to be interpreted by the message parser. Words of text may contain characters from character sets other than ISO 88-59-122. Only when encoded according to the rules of RFC 2047-14, text equals any octet except CTLS, but including LWS, a CRLF is allowed in the definition of text only as part of a header field continuation. It is expected that the folding LWS will be replaced with a single SB before interpretation of the text value. Hexadecimal numeric characters are used in several protocol elements. Hex equals A, B, C, D, field values consist of words separated by LWS or special characters. These special characters must be in a quoted string to be used within a parameter value, as defined in section 3.6. Token equals 1 any char except CTLS or separators equals at slash equals SPHT comments can be included in some HTTP header fields by surrounding the comment text with parentheses. Comments are only allowed in fields containing comment as part of their field value definition. In all other fields, parentheses are considered part of the field value. Comment equals ctext quoted pair comment. Ctext equals any text excluding, and a string of text is parsed as a single word if it is quoted using double quote marks. Quoted string equals QD text quoted pair. QD text equals any text except the backslash character may be used as a single character quoting mechanism only within quoted string and comment constructs. Quoted pair equals char 3 protocol parameters 3.1 HTTP version. HTTP uses a major minor numbering scheme to indicate versions of the protocol. The protocol versioning policy is intended to allow the sender to indicate the format of a message and its capacity for understanding further HTTP communication, rather than the features obtained via that communication. No change is made to the version number for the addition of message components which do not affect communication behavior, or which only add to extensible field values. The minor number is incremented when the changes made to the protocol add features, which do not change the general message parsing algorithm, but which may add to the message semantics and imply additional capabilities of the sender. The major number is incremented when the format of a message within the protocol is changed. See RFC 214536 for a fuller explanation. The version of an HTTP message is indicated by an HTTP version field in the first line of the message. HTTP version equals HTTP / 1 digit. 1 digit. Note that the major and minor numbers must be treated as separate integers, and that each may be incremented higher than a single digit. Thus, HTTP / 2.4 is a lower version than HTTP / 2.13, which in turn is lower than HTTP / 12.3, leading zeros must be ignored by recipients and must not be sent. An application that sends a request or response message that includes HTTP version of HTTP/1.1 must be at least conditionally compliant with this specification. Applications that are at least conditionally compliant with this specification should use an HTTP version of HTTP/1.1 in their messages, and must do so for any message that is not compatible with HTTP/1. For more details on when to send specific HTTP version values, see RFC 214536. The HTTP version of an application is the highest HTTP version for which the application is at least conditionally compliant. Proxy and gateway applications need to be careful when forwarding messages in protocol versions different from that of the application. Since the protocol version indicates the protocol capability of the sender, a proxy/gateway must not send a message with a version indicator which is greater than its actual version. If a higher version request is received, the proxy/gateway must either downgrade the request version or respond with an error or switch to tunnel behavior due to interoperability problems with HTTP/1 proxies discovered since the publication of RFC 206833. Caching proxies must, gateways may, and tunnels must not upgrade the request to the highest version they support. The proxy/gateway's response to that request must be in the same major version as the request. Note: converting between versions of HTTP may involve modification of header fields required or forbidden by the versions involved. URIs have been known by many names, such as www addresses, Universal Document Identifiers, Universal Resource Identifiers 3, and finally, the combination of Uniform Resource Locators, URL, for, and names. Earn 20. As far as HTTP is concerned, Uniform Resource Identifiers are simply formatted strings which identify a resource via name, location, or any other characteristic. 3.21 General Syntax. URIs in HTTP can be represented in absolute form or relative to some known base URI 11. Depending upon the context of their use. The two forms are differentiated by the fact that absolute URIs always begin with a scheme name followed by a colon. For definitive information on URL syntax and semantics, see Uniform Resource Identifiers, URI, Generic Syntax and Semantics, RFC 2396-42, which replaces RFCS 1738-4 and RFC 18-811. This specification adopts the definitions of URI reference, absolute URI, relative URI, port, host, ABS path, rel path, and authority from that specification. The HTTP protocol does not place any a priori limit on the length of a URI. Servers must be able to handle the URI of any resource they serve, and should be able to handle URIs of unbounded length if they provide GET-based forms that could generate such URIs. A server should return 414. Request URI too long. Status: if a URI is longer than the server can handle, see section 10.415. Note: servers ought to be cautious about depending on URI lengths above 255 bytes, because some older client or proxy implementations might not properly support these lengths. 3.22 HTTP URL. The HTTP scheme is used to locate network resources via the HTTP protocol. This section defines the scheme-specific syntax and semantics for HTTP URLs. HTTP URL equals HTTP//host port ABS path. Query: if the port is empty or not given, port 80 is assumed. The semantics are that the identified resource is located at the server, listening for TCP connections on that port of that host, and the request URI for the resource is ABS path. Section 5.12. The use of IP addresses in URLs should be avoided whenever possible. See RFC 19.0.24. If the ABS path is not present in the URL, it must be given as / when used as a request URI for a resource. Section 5.12. If a proxy receives a host name which is not a fully qualified domain name, it may add its domain to the host name it received. If a proxy receives a fully qualified domain name, the proxy must not change the host name. 3.23 URI comparison. when comparing two URIs to decide if they match or not. A client should use a case-sensitive octet-by-octet comparison of the entire URIs. With these exceptions, a port that is empty or not given is equivalent to the default port for that URI reference. Comparisons of host names must be case-insensitive. Comparisons of scheme names must be case-insensitive. An empty ABS path is equivalent to an ABS path of /. Characters other than those in the reserved and unsafe sets, see RFC 2396-42, are equivalent to their %hex encoding. For example, the following three URIs are equivalent: http://abc.com:80/smith/home.html, http://abc.com/%, 7smith/home.html, http://abc.com/%, 7smith/home.html. 3.3 date/time. Formats: 3.31 full date HTTP applications have historically allowed three different formats for the representation of date/time stamps. Sun 6 Nov 1994 8:49 and 37 seconds GMT. RFC 822, updated by RFC 1000, 123 Sunday, 6 Nov 94 8:49 and 37 seconds GMT. RFC 850, obsoleted by RFC 1000, and 36 Sun, Nov 6 8:49 and 37 seconds 1994 ANSI CS ISK time. Format: the first format is preferred as an internet standard and represents a fixed length subset of that defined by RFC 1000, 123.8, an update to RFC 822. 9. The second format is in common use, but is based on the obsolete RFC 850-12 date format and lacks a 4-digit year. HTTP/1.1 clients and servers that parse the date value must accept all three formats for compatibility with HTTP/1, though they must only generate the RFC 1000, 123 format for representing HTTP date values in header fields. See section 19.3 for further information. Recipients of date values are encouraged to be robust in accepting date values that may have been sent by non-HTTP applications, as is sometimes the case when retrieving or posting messages via proxies/gateways to SMTP or NNTP. All HTTP date/timestamps must be represented in Greenwich Mean Time, GMT, without exception. For the purposes of HTTP, GMT is exactly equal to UTC, Coordinated Universal Time. This is indicated in the first two formats by the inclusion of GMT as the three-letter abbreviation for time zone, and must be assumed when reading the ISK time format. HTTP date is case sensitive and must not include additional LWS beyond that specifically included as SB in the grammar. HTTP date equals RFCN 1000, 123 date RFC 800, and 50 date ISK time date RFCN 1000. 123 date equals WK day, SB Daytone, SB time, SB GMT, RFC 800, and 50 date equals weekday, SB Datatwo, SB time, SB GMT. ISK time date equals WK day, SB data 3, SB time, SB 4, digit Daytone equals 2-digit SB month, SB 4 digit day, month, year, e.g. 2 Jun 1982 Datatwo equals 2-digit month, 2-digit day, month, year, e.g. 2 Jun 82 data 3 equals month, SB 2-digit SB 1-digit month, day, e.g. Jun 2 time equals 2-digit 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 0 and 0 seconds, 23:59 and 59 seconds. WK day equals Moan, 2 wed, thur, fry, sat, sun, weekday equals Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, month equals Jan, Feb, Mar, April, May, Jun, Jul, Aug, Sep, Oct, Nov, Dec, Note. HTTP requirements for the date/time stamp format apply only to their usage within the protocol stream. Clients and servers are not required to use these formats for user presentation, request logging, etc. 3.32 delta seconds. Some HTTP header fields allow a time value to be specified as an integer number of seconds, represented in decimal, after the time that the message was received. Delta seconds equals 1-digit 3.4 character sets. HTTP uses the same definition of the term character set as that described for MIME. The term character set is used in this document to refer to a method used with 1, or more tables to convert a sequence of octets into a sequence of characters. Note that unconditional conversion in the other direction is not required, in that not all characters may be available in a given character set, and a character set may provide more than one sequence of octets to represent a particular character. This definition is intended to allow various kinds of character encoding, from simple single-table mappings, such as US ASCII, to complex table switching methods, such as those that use is ominous 2022's techniques. However, the definition associated with a MIME character set name must fully specify the mapping to be performed from octets to characters. In particular, use of external profiling information to determine the exact mapping is not permitted. Note, this use of the term character set is more commonly referred to as a character encoding. However, since HTTP and MIME share the same registry, it is important that the terminology also be shared. HTTP character sets are identified by case-insensitive tokens. The complete set of tokens is defined by the IANA character set registry 19 charset equals token. Although HTTP allows an arbitrary token to be used as a charset value, any token that has a predefined value within the IANA character set registry 19 must represent the character set defined by that registry. Applications should limit their use of character sets to those defined by the IANA registry. Implementors should be aware of IETF character set requirements 3841. Note, recipients are encouraged to include a charset parameter even when the charset is ominous 8,859-1 and SHOULD. Do so when it is known that it will not confuse the recipient. Unfortunately, some older HTTP/1 clients did not deal properly with an explicit charset parameter. HTTP/1.1 recipients must respect the charset label provided by the sender and those user agents that have a provision to guess. A charset must use the charset from the content type field if they support that charset, rather than the recipient's preference when initially displaying a document. See section 3.71. Content coding values indicate an encoding transformation that has been or can be applied to an entity. Content codings are primarily used to allow a document to be compressed or otherwise usefully transformed without losing the identity of its underlying media type and without loss of information. Frequently, the entity is stored in coded form, transmitted directly, and only decoded by the recipient. Content coding equals token. All content coding values are case insensitive. HTTP/1.1 uses content coding values in the accepting coding section 14.3 and content encoding section 14.11 header fields. Although the value describes the content coding, what is more important is that it indicates what decoding mechanism will be required to remove the encoding. The Internet Assigned Numbers Authority, IANA, acts as a registry for content coding value tokens. Initially, the registry contains the following tokens: gzip, an encoding format produced by the file compression program; gzip, GNU-zip, as described in RFC 1952-25. This format is a Limpel-ziv coding, L77, with a 32-bit CRC. Compress the encoding format produced by the common Unix file compression program, Compress. This format is an adaptive Limpel-ziv-Welch coding, LZW. Use of program names for the identification of encoding formats is not desirable and is discouraged for future encodings. Their use here is representative of historical practice, not good design. For compatibility with previous implementations of HTTP, applications should consider xgzip and xcompress to be equivalent to gzip and compress, respectively. Deflate the zlib format defined in RFC 1950-31 in combination with the deflate compression mechanism described in RFC 1951-29. Identity, the default identity, encoding, the use of no transformation whatsoever. This content coding is used only in the accepting coding header and should not be used in the content encoding header. New content coding value tokens should be registered to allow interoperability between clients and servers. Specifications of the content coding algorithms needed to implement a new value should be publicly available and adequate for independent implementation and conform to the purpose of content coding defined in this section. Transfer coding values. are used to indicate an encoding transformation that has been, can be, or may need to be applied to an entity body in order to ensure safe transport through the network. This differs from a content coding in that the transfer coding is a property of the message, not of the original entity. Transfer coding equals chunked. Transfer extension equals token. Parameters are in the form of attribute/value pairs. Parameter equals attribute equals value attribute equals token value equals token quoted string. All transfer coding values are case insensitive. HTTP/1.1 uses transfer coding values in the TE header field, section 14.39, and in the transfer encoding header field, section 14.41. Whenever a transfer coding is applied to a message body, the set of transfer codings must include chunked unless the message is terminated by closing the connection. When the chunked transfer coding is used, it must be the last transfer coding applied to the message body. The chunked transfer coding must not be applied more than once to a message body. These rules allow the recipient to determine the transfer length of the message. Section 4.4. Transfer codings are analogous to the content transfer encoding values of MIME 7, which were designed to enable safe transport of binary data over a 7-bit transport service. However, safe transport has a different focus for an 8-bit clean transfer protocol. In HTTP, the only unsafe characteristic of message bodies is the difficulty in determining the exact body length. Section 7.22, or the desire to encrypt data over a shared transport. The Internet Assigned Numbers Authority, IANA, acts as a registry for transfer coding value tokens. Initially, the registry contains the following tokens: chunked, section 3.61, identity, section 3.62, gzip, section 3.5, compress, section 3.5, and deflate, section 3.5. New transfer coding value tokens should be registered in the same way as new content coding value tokens. Section 3.5. A server which receives an entity body with a transfer coding. It does not understand SHOULD return 501 unimplemented and close the connection. A server must not send transfer codings to an HTTP/1 client. 3.61 chunked transfer coding. The chunked encoding modifies the body of a message in order to transfer it as a series of chunks, each with its own size indicator, followed by an optional trailer containing entity header fields. This allows dynamically produced content to be transferred along with the information necessary for the recipient to verify that it has received the full message. Chunked body equals chunk, last chunk trailer CRLF chunk equals chunk size, chunk extension, CRLF chunk data CRLF chunk size equals 1 hex last chunk equals 1, 0 chunk extension, CRLF chunk extension equals chunkext name equals chunkextval, chunkext name equals token chunkextval equals token quoted string, chunk data equals chunk size, octet trailer equals entity header CRLF. The chunk size field is a string of hex digits indicating the size of the chunk. The chunked encoding is ended by any chunk whose size is 0, followed by the trailer, which is terminated by an empty line. The trailer allows the sender to include additional HTTP header fields at the end of the message. The trailer header field can be used to indicate which header fields are included in a trailer C section 14.4. A server using chunked transfer coding in a response must not use the trailer for any header fields unless at least one of the following is true. A. The request included a TE header field that indicates trailers is acceptable in the transfer coding of the response as described in section 14.39, or B. The server is the origin server for the response. The trailer fields consist entirely of optional metadata, and the recipient could use the message in a manner acceptable to the origin server without receiving this metadata. In other words, the origin server is willing to accept the possibility that the trailer fields might be silently discarded along the path to the client. This requirement prevents an interoperability failure when the message is being received by an HTTP/1.1 or later proxy and forwarded to an HTTP/1 recipient. It avoids a situation where compliance with the protocol would have necessitated a possibly infinite buffer on the proxy. An example process for decoding a chunked body is presented in Appendix 19.46. All HTTP/1.1 applications must be able to receive and decode the chunked transfer coding, and must ignore chunk extension extensions they do not understand. Media types are used in HTTP. HTTP uses Internet Media Types 17 in the Content Type section 14.17 and except section 14.1. Header fields to provide open and extensible data typing and type negotiation. Media type equals type / subtype. Parameter type equals token subtype equals token parameters may follow the type / subtype in the form of attribute / value pairs as defined in section 3.6. The type subtype and parameter attribute names are case insensitive. Parameter values might or might not be case sensitive depending on the semantics of the parameter name. Linear white space LWS must not be used between the type and subtype, nor between an attribute and its value. The presence or absence of a parameter might be significant to the processing of a media type, depending on its definition within the media type registry. Note that some older HTTP applications do not recognize media type parameters. When sending data to older HTTP applications, implementations should only use media type parameters when they are required by that type subtype definition. Media type values are registered with the Internet Assigned Number Authority IANA 19. The media type registration process is outlined in RFC 1590. 17. Use of non-registered media types is discouraged. 3.71 Canonicalization and text defaults. Internet media types are registered with a canonical form. An entity body transferred via HTTP messages must be represented in the appropriate canonical form prior to its transmission, except for text types as defined in the next paragraph. When in canonical form, media subtypes of the text type use CRLF as the text line break. HTTP relaxes this requirement and allows the transport of text media with plain CR or LF alone, representing a line break when it is done consistently for an entire entity body. HTTP applications must accept CRLF bare CR and bare LF as being representative of a line break in text media received via HTTP. In addition, if the text is represented in a character set that does not use octets 13 and 10 for CR and LF, respectively, as is the case for some multi-byte character sets. HTTP allows the use of whatever octet sequences are defined by that character set to represent the equivalent of CR and LF for line breaks. This flexibility regarding line breaks applies only to text media in the entity body. A bare CR or LF must not be substituted for CRLF within any of the HTTP control structures, such as header fields and multi-part boundaries. If an entity body is encoded with a content coding, the underlying data must be in a form defined above prior to being encoded. The charset parameter is used with some media types to define the character set section 3.4 of the data when no explicit charset parameter is provided by the sender media subtypes of the text type are defined to have a default charset value of is ominous 8,859-1 when received via HTTP. Data in character sets other than is ominous 8,859-1 or its subsets must be labeled with an appropriate charset value. See section 3.41 for compatibility problems. 3.72 multi-part types. MIME provides for a number of multi-part types encapsulations of one or more entities within a single message body. All multi-part types share a common syntax as defined in section 5.11 of RFC 2046-40 and must include a boundary parameter as part of the media type value. The message body is itself a protocol element and must therefore use only CRLF to represent line breaks between body parts. Unlike in RFC 2046, the epilogue of any multi-part message must be empty. HTTP applications must not transmit the epilogue, even if the original multi-part contains an epilogue. These restrictions exist in order to preserve the self-delimiting nature of a multi-part message body, wherein the end of the message body is indicated by the ending multi-part boundary. In general, HTTP treats a multi-part message body no differently than any other media type strictly as payload. The one exception is the multi-part byte ranges type appendix 19.2 when it appears in a 206 partial content response, which will be interpreted by some HTTP caching mechanisms as described in sections 13.54 and 14.16. In all other cases, an HTTP user agent should follow the same or similar behavior as a MIME user agent would upon receipt of a multi-part type. The MIME header fields within each body part of a multi-part message body do not have any significance to HTTP beyond that defined by their MIME semantics. In general, an HTTP user agent should follow the same or similar behavior as a MIME user agent would upon receipt of a multi-part type. If an application receives an unrecognized multi-part subtype, the application must treat it as being equivalent to multi-part/mixed. Note, the multi-part/form data type has been specifically defined for carrying form data suitable for processing via the post request method as described in RFC 1867 product tokens used to allow communicating applications to identify themselves by software name and version most fields using product tokens. Also allow subproducts, which form a significant part of the application, to be listed separated by white space by convention. The products are listed in order of their significance for identifying the application product. Token equals token optional / product version equals token examples user agent CERN line mode 200 and 15 libWA 217 B3 server Apache 84 product tokens should be short and to the point. They must not be used for advertising or other non-essential information, although any token character may appear in a product version. This token should only be used for a version identifier, i.e. successive versions of the same product should only differ in the product version portion of the product value quality. Values HTTP content negotiation uses short floating point numbers to indicate the relative importance weight of various negotiable parameters. A weight is normalized to a real number in the range 0 through 1, where 0 is the minimum and 1 the maximum value. If a parameter has a quality value of 0, then content with this parameter is not acceptable for the client HTTP11 applications, must not generate more than 3 digits after the decimal point. User configuration of these values should also be limited in this fashion: Q value 0 optional period 0 to 3 digit, or 1 optional period 0 to 3 zeros quality values, is a misnomer, since these values merely represent relative degradation in desired quality language tags. Identify a natural language spoken, written, or otherwise conveyed by human beings for communication of information to other human beings. Computer languages are explicitly excluded. HTTP uses language tags within the accept language and content language fields. The syntax and registry of HTTP language tags is the same as that defined by RFC 1766. In summary, a language tag is composed of one or more parts: a primary language tag and a possibly empty series of subtags. Language tag equals primary tag optional minus subtag primary tag equals 1 to 8 alphabetical characters subtag equals 1 to 8 alphabetical characters. White space is not allowed within the tag, and all tags are case insensitive. The namespace language tags is administered by the IANA example tags. Include N, NUS, N Cockney, I Cherokee, X Big Latin, where any two-letter primary tag is ominous 639 language abbreviation, and any two-letter initial subtag is ominous 3166 country. Code. The last three tags above are not registered tags. All but the last are examples of tags which could be registered in future. Entity tags are used for comparing two or more entities from the same requested resource. HTTP uses entity tags in the E-tag, if match, if none match, and if range header fields. The definition of how they are used and compared as cache validators is in section 1333. An entity tag consists of an opaque quoted string, possibly prefixed by a weakness indicator entity tag, equals optional weak opaque tag, weak equals w/opaque tag, equals quoted string. A strong entity tag may be shared by two entities of a resource only if they are equivalent by octet equality. A weak entity tag, indicated by the W prefix, may be shared by two entities of a resource only if the entities are equivalent, and could be substituted each other with no significant change in semantics. A weak entity tag can only be used for weak comparison. An entity tag must be unique across all versions of all entities associated with a particular resource. A given entity tag value may be used for entities obtained by requests on different URIs. The use of the same entity tag value in conjunction with entities obtained by requests on different URIs does not imply the equivalence of those entities. 3.12 range units HTTP/1.1 allows a client to request that only part, a range of the response entity, be included within the response. HTTP/1.1 uses range units in the range section 14.35 and content range section 14.16. Header fields, an entity, can be broken down into subranges according to various structural units. Range unit equals bytes unit, other range unit bytes unit equals bytes. Other range unit equals token, the only range unit defined by http/1.1 is bytes. http/1.1 implementations may ignore ranges specified using other units. http/1.1 has been designed to allow implementations of applications that do not depend on knowledge of ranges. For HTTP message 4.1 message types, HTTP messages consist of requests from client to server and responses from server to client. HTTP message equals request response. HTTP/1.1 messages request, section 5, and response, section 6, messages use the generic message format of RFC 822. 9. For transferring entities, the payload of the message. Both types of message consist of a start line, 0 or more header fields, also known as headers, an empty line, i.e., a line with nothing preceding the CRLF, indicating the end of the header fields, and possibly a message body. Generic message equals start line message header CRLF. CRLF message body start line equals request line status line in the interest of robustness. Servers should ignore any empty lines received where a request line is expected. In other words, if the server is reading the protocol stream at the beginning of a message and receives a CRLF first, it should ignore the CRLF. Certain buggy HTTP/1 client implementations generate extra CRLFs after a post request to restate what is explicitly forbidden by the BNF. An HTTP/1.1 client must not preface or follow a request with an extra CRLF. 4.2 message headers HTTP header fields, which include general header section 4.5, request header section 5.3, response header section 6.2, and entity header section 7.1 fields follow the same generic format as that given in section 3.1 of RFC 822. 9. Each header field consists of a name followed by a colon and the field value. Field names are case insensitive. The field value may be preceded by any amount of LWS. Though a single SB is preferred, header fields can be extended over multiple lines by preceding each extra line with at least one SB or HT. Applications ought to follow common form, where one is known or indicated when generating HTTP constructs, since there might exist some implementations that fail to accept anything beyond the common forms. Message header equals field name. Field value field name equals token field value equals field content LWS. Field content equals the octets making up the field value, and consisting of either text or combinations of token, separators, and quoted string. The field content does not include any leading or trailing LWS, linear white space, occurring before the first non-white space character of the field value, or after the last non-white space character of the field value. Such leading or trailing LWS may be removed without changing the semantics of the field value. Any LWS that occurs between field content may be replaced with a single SB before interpreting the field value or forwarding the message downstream. The order in which header fields with differing field names are received is not significant. However, it is good practice to send general header fields first, followed by request header or response header fields, and ending with the entity header fields. Multiple message header fields with the same field name may be present in a message, if and only if the entire field value for that header field is defined as a comma-separated list, i.e., number values. It must be possible to combine the multiple header fields into one field name, field value pair, without changing the semantics of the message, by appending each subsequent field value to the first, each separated by a comma. The order in which header fields with the same field name are received is therefore significant to the interpretation of the combined field value, and thus a proxy must not change the order of these field values when a message is forwarded. 4.3 Message body. The message body, if any of an HTTP message, is used to carry the entity body associated with the request or response. The message body differs from the entity body only when a transfer coding has been applied, as indicated by the transfer encoding header field, section 14.41. Message body equals entity body encoded as per transferring coding must be used to indicate any transfer codings applied by an application to ensure safe and proper transfer of the message. Transferring coding is a property of the message, not of the entity, and thus may be added or removed by any application along the request/response chain. However, Section 3.6 places restrictions on when certain transfer codings may be used. The rules for when a message body is allowed in a message differ for requests and responses. The presence of a message body in a request is signaled by the inclusion of a content length or transferring coding header field in the request's message headers. A message body must not be included in a request if the specification of the request method, Section 5.11, does not allow sending an entity body in requests. A server should read and forward a message body on any request if the request method does not include defined semantics for an entity body. Then the message body should be ignored when handling the request for response messages. Whether or not a message body is included with a message is dependent on both the request method and the response status code. Section 6.11. All responses to the head request method must not include a message body, even though the presence of entity header fields might lead one to believe they do. All 1XX informational 204 no content and 304 not modified responses must not include a message body. All other responses do include a message body, although it may be of 0 length. 4.4 message length. The transfer length of a message is the length of the message body as it appears in the message, that is, after any transfer codings have been applied. When a message body is included with a message, the transfer length of that body is determined by one of the following in order of precedence: any response message which must not include a message body, such as the 1XX, 204, and 304 responses, and any response to a head request is always terminated by the first empty line after the header fields, regardless of the entity header fields present in the message. If a transferring coding header field, Section 14.41, is present and has any value other than identity, then the transfer length is defined by use of the chunked transfer coding section 3.6. unless the message is terminated by closing the connection. If a content length header field, section 14.13, is present, its decimal value in octets represents both the entity length and the transfer length. The content length header field must not be sent if these two lengths are different, i.e., if a transfer encoding header field is present, the content length header field must not be sent if these two lengths are different, i.e., if a transfer encoding header field is present. If a message is received with both a transfer encoding header field and a content length header field, the latter must be ignored. For if the message uses the media type multipart byte ranges and the transfer length is not otherwise specified, then this self-limiting media type defines the transfer length. This media type must not be used unless the sender knows that the recipient can parse it the presence in a request of a range header with multiple byte range specifiers from a 1.1 client implies that the client can parse multi-part byte ranges. Responses a range header might be forwarded by a one proxy that does not understand multi-part byte ranges. In this case, the server must delimit the message using methods defined in items 1, 3, or 5 of this section. By the server closing the connection cannot be used to indicate the end of a request body, since that would leave no possibility for the server to send back a response for compatibility with HTTP1 applications. HTTP 1.1 requests containing a message body must include a valid content length header field unless the server is known to be HTTP 1.1 compliant. If a request contains a message body and a content length is not given, the server should respond with 400 bad request if it cannot determine the length of the message, or with 411 length required if it wishes to insist on receiving a valid content length. All HTTP 1.1 applications that receive entities must accept the chunked transfer coding section 3.6, thus allowing this mechanism to be used for messages when the message length cannot be determined in advance. Messages must not include both a content length header field and a non-identity transfer coding. If the message does include a non-identity transfer coding, the content length must be ignored when a content length is given in a message where a message body is allowed. Its field value must exactly match the number of octets in the message body. HTTP 1.1 user agents must notify the user invalid length is received and detected 4.5 general header fields. There are a few header fields which have general applicability for both request and response messages, but which do not apply to the entity being transferred. These header fields apply only to the general header equals cache control section, 14.9 connection section, 14.1 date section, 14.1 8 pragma section, 14.3 2 trailer section, 14.4 transfer encoding section, 14.41 upgrade section, 14.42 via section, 14.45 warning section, 14.46 general header field names can be extended reliably only in combination with a change in the protocol version. However, new or experimental header fields may be given the semantics of general header fields if all parties in the communication recognize them to be general header fields. Unrecognized header fields are treated as entity header. Yields 5 request a request message from a client to a server. Includes within the first line of that message the method to be applied to the resource, the identifier of the resource, and the protocol version in use request equals request line section 5.1, general header section 4.5, request header section 5.3, entity header CRLF section 7.1, CRLF, message body section 4.3, 5.1, request line. The request line begins with a method token followed by the request URI and the protocol version, and ending with CRLF. The elements are separated by SB characters. No CR or LF is allowed except in the final CRLF sequence. Request line equals method SB request URI SB HTTP version CRLF 5.11 method. The method token indicates the method to be performed on the resource identified by the request URI. The method is case sensitive. Method equals options. Section 9.2 get. Section 9.3 head. Section 9.4 post. Section 9.5 put. Section 9.6 delete. Section 9.7 trace. Section 9.8 connect. Section 9.9 extension method. Extension method equals token. The list of methods allowed by a resource can be specified in an allow header field. Section 14.7 the return code of the response always notifies the client whether a method is currently allowed on a resource. Since the set of allowed methods can change dynamically, an origin server SHOULD return the status code 405 method not allowed. If the method is known by the origin server but not allowed for for the requested resource. And 501. Not implemented if the method is unrecognized or not implemented by the origin server. The methods get and head must be supported by all general-purpose servers. All other methods are optional, however. If the above methods are implemented, they must be implemented with the same semantics as those specified in Section 9, 5.12, Request URI. The request URI is a uniform resource identifier, Section 3.2, and identifies the resource upon which to apply the request. Request URI equals absolute URI abs path authority. The four options for request URI are dependent on the nature of the request. The asterisk means that the request does not apply to a particular resource, but to the server itself, and is only allowed when the method used does not necessarily apply to a resource. One example would be options http:/1.1. The absolute URI form is required when the request is being made to a proxy. The proxy is requested to forward the request or service it from a valid cache and return the response. Note that the proxy may forward the request on to another proxy or directly to the server specified by the absolute URI. In order to avoid request loops, a proxy must be able to recognize all of its server names, including any aliases, local variations, and the numeric IP address. An example request line would be get http www.w3.org/pub/the project.html http:/1.1 to allow for transition to absolute URIs in all requests in future versions of HTTP. All HTTP:1.1 servers must accept the absolute URI form in requests, even though HTTP:1.1 clients will only generate them in requests to proxies. The authority form is only used by the connect method. Section 9.9. The most common form of request URI is that used to identify a resource on an origin server or gateway. In this case, the absolute path of the URI must be transmitted. See Section 3.21, abs path, as the request URI, and the network location of the URI authority must be transmitted in a host header field. For example, a client wishing to retrieve the resource above directly from the origin server would create a TCP connection to port 80 of the host, www.w3.org, and send the lines get/pub/www/ the project HTML http:/1.1 host www.w3.org, followed by the remainder of the request. Note that the absolute path cannot be empty. If none is present in the original URI, it must be given as / the server root. The request URI is transmitted in the format specified in section 3.21. If the request URI is encoded using the %hex encoding 42, the origin server must decode the request URI in order to properly interpret the request. Servers should respond to invalid request URIs with an appropriate status code. A transparent proxy must not rewrite the ABS path, part of the received request URI, when forwarding it to the next inbound server, except as noted above, to replace a null ABS path with /. Note, the no rewrite rule prevents the proxy from changing the meaning of the request when the origin server is improperly using a non-reserved URI character for a reserved purpose. Implementors should be aware that some pre-HTTP/1.1 proxies have been known to rewrite the request URI. The exact resource identified by an internet request is determined by examining both the request URI and the host header field. An origin server that does not allow resources to differ by the requested host may ignore the host header field value when determining the resource identified by an HTTP/1.1 request, but see section 19.6.1.1 for other requirements on host support in HTTP/1.1. An origin server that does differentiate resources based on the host requested, sometimes referred to as virtual hosts or vanity host names, must use the following rules for determining the requested resource on an HTTP/1.1 request. If request URI is an absolute URI, the host is part of the request URI. Any host header field value in the request must be ignored. If the request URI is not an absolute URI and the request includes a host header field, the host is determined by the host header field value. If the host as determined by Rule 1 or 2 is not a valid host on the server, The response must be a 400 bad request error message. Recipients of an HTTP/1 request that lacks a host header field may attempt to use heuristics, e.g., examination of the URI path for something unique to a particular host in order to determine what exact resource is being requested. 5.3 Request Header Fields. The request header fields allow the client to pass additional information about the request and about the client itself to the server. These fields act as request modifiers with semantics equivalent to the parameters on a programming language method invocation. Request header equals accept. Section 14.1 Accept charset. Section 14.2 Accepting coding. Section 14.3 Accept language. Section 14.4 Authorization. Section 14.8 Expect. Section 14.2 From. Section 14.22 Host. Section 14.23 If match. Section 14.24 If modified since. Section 14.25 If none match. Section 14.26 If range. Section 14.27 If unmodified since. Section 14.28 Max forwards. Section 14.31 Proxy authorization. Section 14.34 Range. Section 14.35 Refer. Section 14.36 Section 14.39 User agent. Section 14.43 Request header field names can be extended reliably only in combination with a change in the protocol version. However, new or experimental header fields may be given the semantics of request header fields if all parties in the communication recognize them to be request header fields. Unrecognized header fields are treated as entity header fields. 6. Response after receiving and interpreting a request message. A server responds with an HTTP response message. Response equals status line. Section 6.1 A general header. Section 4.5 Response header. Section 6.2 Entity header, CRLF. Section 7.1 CRLF Message body. Section 7.2 6.1 Status line. The first line of a response message is the status line, consisting of the protocol version followed by a numeric status code and its associated textual phrase, with each element separated by SB characters. No CR or LF is allowed except in the final CRLF sequence. Status line equals HTTP version, SB status code SB, reason phrase CRLF, 6.11 status code, and reason phrase. The status code element is a 3-digit integer result code of the attempt to understand and satisfy the request. These codes are fully defined in Section 10. The reason phrase is intended to give a short textual description of the status code. The status code is intended for use by automata, and the reason phrase is intended for the human user. The client is not required to examine or display the reason phrase. The first digit of the status code defines the class of response. The last 2 digits do not have any categorization role. There are 5 values for the first digit. POS2 1XX informational request received. Continuing process 2XX success. The action was successfully received, understood, and accepted. 3XX redirection, further action, must be taken in order to complete the request. 4XX client error. The request contains bad syntax or cannot be fulfilled. 5XX server error. The server failed to fulfill an apparently valid request. The individual values of the numeric status codes defined for HTTP/1.1 and an example set of corresponding reason phrases are presented below. The reason phrases listed here are only recommendations. They may be replaced by local equivalents without affecting the protocol. Status code equals POS2 100 section 10.11. Continue 101 section 10.12. Switching protocols 200 section 10.21. OK 201 section 10.22. Created 202 section 10.23. Accepted 203 section 10.24. Non-authoritative information 204 section 10.25. No content 205 section 10.26. Reset content 206 section 10.27. Partial content 300 section 10.31. Multiple choices 301 section 10.32. Moved permanently 302 section 10.33. Found 303 section 10.34. See other 304 section 10.35. Not modified 305 section 10.36. Use proxy 307 section 10.38. Temporary redirect 400, Section 10.41, bad request. 401, Section 10.42, unauthorized. 402, Section 10.43, payment required. 403, Section 10.44, forbidden. 404, Section 10.45, not found. 405, Section 10.46, method not allowed. 406, Section 10.47, not acceptable. 407, Section 10.48, proxy authentication required. 408, Section 10.49, request timeout. 409, Section 10.410, conflict. 410, Section 10.411, gone. 411, Section 10.412, length required. 412, Section 10.413, precondition failed. 413, Section 10.414, quest entity too large. 414, Section 10.415, request URI too large. 415, Section 10.416, unsupported media type. 416, Section 10.417, requested range not satisfiable. 417, Section 10.418, expectation failed. 500, Section 10.51, internal server error. 501, Section 10.52, not implemented. 502, Section 10.53, bad gateway. 503, Section 10.54, service unavailable. 504, Section 10.55, gateway timeout. 505, Section 10.56, HTTP version not supported. Extension code pause 2. Extension code equals 3-digit reason phrase equals text excluding CRLF. HTTP status codes are extensible. HTTP applications are not required to understand the meaning of all registered status codes, though such understanding is obviously desirable. However, applications must understand the class of any status code as indicated by the first digit and treat any unrecognized response as being equivalent to the X0 status code of that class, with the exception that an unrecognized response must not be cached. For example, if an unrecognized status code of 431 is received by the client, it can safely assume that there was something wrong with its request and treat the response as if it had received a 400 status code. In such cases, user agents should present to the user the entity returned with the response, since that entity is likely to include human-readable information which will explain the unusual status. 6.2 Response Header Fields. The response header fields allow the server to pass additional information about the response, which cannot be placed in the status line. These header fields give information about the server and about further access to the resource identified by the request URI. Response header equals accept ranges. Section 14.5 age. Section 14.6 etag. Section 14.19 location. Section 14.3 proxy authenticate. Section 14.33 retry after. Section 14.37 server. Section 14.38 vary. Section 14.44 www authenticate. Section 14.47 response header field names can be extended reliably only in combination with a change in the protocol version. However, new or experimental header fields may be given the semantics of response header fields if all parties in the communication recognize them to be response header fields. Unrecognized header fields are treated as entity header fields. 7 entity request and response messages may transfer an entity if not otherwise restricted by the request method or response status code. An entity consists of entity header fields and an entity body, although some responses will only include the entity headers. In this section, both sender and recipient refer to either the client or the server, depending on who sends and who receives the entity. 7.1 Entity header fields. Entity header fields define meta-information about the entity body, or, if no body is present, about the resource identified by the request. Some of this meta-information is optional. Some might be required by portions of this specification. Entity header equals allow. Section 14.7 Content encoding. Section 14.11 Content language. Section 14.12 Content length. Section 14.13 Content location. Section 14.14 Content MD5. Section 14.15 Content train. Section 14.16 Content type. Section 14.17 Expires. Section 14.21 Last modified. Section 14.29 Extension header. Extension header equals message header. The extension header mechanism allows additional entity header fields to be defined without changing the protocol. But these fields cannot be assumed to be recognizable by the recipient. Unrecognized header fields should be ignored by the recipient and must be forwarded by transparent proxies. 7.2 Entity Body. The entity body. If any sent with an HTTP request or response is in a format and encoding defined by the entity header fields, entity body equals octet, and entity body is only present in a message when a message body is present, as described in section 4.3. The entity body is obtained from the message body by decoding any transfer encoding that might have been applied to ensure safe and proper transfer of the message. 7.21 Type. When an entity body is included with a message, the data type of that body is determined via the header field's content type. And content encoding, these define a two-layer ordered encoding model entity body equals content encoding content type, data content type. Specifies the media type of the underlying data content encoding, may be used to indicate any additional content codings applied to the data, usually for the purpose of data compression, that are a property of the requested resource. There is no default encoding any HTTP/1.1 message containing an entity body, SHOULD. Include a content type header field defining the media type of that body if, and only if, the media type is not given by a content type field. The recipient may attempt to guess the media type via inspection of its content, and or the name extensions of the URI used to identify the resource. If the media type remains unknown, the recipient should treat it as type application / octet stream. 722 Entity length. The entity length of a message is the length of the message body before any transfer codings have been applied. Section 4.4 defines how the transfer length of a message body is determined. 8 connections, 8.1 persistent connections, 8.1.1 purpose prior to persistent connections. A separate TCP connection was established to fetch each URL, increasing the load on HTTP servers and causing congestion on the internet. The use of inline images and other associated data often require a client to make multiple requests of the same server. In a short amount of time, analysis of these performance problems and results from a prototype implementation are available. 2630 implementation experience and measurements of actual HTTP/11 RFC 2068 implementations show good results. 39 alternatives have also been explored, for example T/TCP, 27 persistent HTTP connections have a number of advantages. By opening and closing fewer TCP connections, CPU time is saved in routers and hosts, clients, servers, proxies, gateways, tunnels, or caches and memory used for TCP protocol control blocks can be saved in hosts. HTTP requests and responses can be pipelined on a connection. Pipelining allows a client to make multiple requests without waiting for each response, allowing a single TCP connection to be used much more efficiently with much lower elapsed time. Network congestion is reduced by reducing the number of packets caused by TCP opens and by allowing TCP sufficient time to determine the congestion state of the network latency on subsequent requests is reduced. Since there is no time spent in TCP/S connection, opening handshake HTTP can evolve more gracefully, since errors can be reported without the penalty of closing the TCP connection. Clients using future versions of HTTP might optimistically try a new feature. But if communicating with an older server retry with old semantics after an error is reported, HTTP implementations should implement persistent connections. 812 overall operation. A significant difference between HTTP/11 and earlier versions of HTTP is that persistent connections are the default behavior of any HTTP connection. That is, unless otherwise indicated, the client SHOULD assume that the server will maintain persistent connection even after error responses from the server. Persistent connections provide a mechanism by which a client and a server can signal the close of a TCP connection. This signaling takes place using the connection header field section 1410. Once a close has been signaled, the client must not send any more requests on that connection. 8121 negotiation. An HTTP/11 server may assume that a HTTP/11 client intends to maintain a persistent connection unless a connection header, including the connection token close, was sent in the request. If the server chooses to close the connection immediately after sending the response, it should send a connection header, including the connection token close. An HTTP/1.1 client may expect a connection to remain open, but would decide to keep it open based on whether the response from a server contains a connection header with the connection token close. In case the client does not want to maintain a connection for more than that request, it should send a connection header, including the connection token close. If either the client or the server sends the close token in the connection header, that request becomes the last one for the connection. Clients and servers should not assume that a persistent connection is maintained for HTTP versions less than 1.1 unless it is explicitly signaled. See section 19.62 for more information on backward compatibility with HTTP/1 clients. In order to remain persistent, all messages on the connection must have a self-defined message length, i.e., one not defined by closure of the connection, as described in section 4.4 8.1.2.2. Pipelining a client that supports persistent connections may pipeline its requests, i.e., send multiple requests without waiting for each response. A server must send its responses to those requests in the same order that the requests were received. Clients which assume persistent connections and pipeline immediately after connection establishment should be prepared to retry their connection if the first pipelined attempt fails. If a client does such a retry, it must not pipeline before it knows the connection is persistent. Clients must also be prepared to resend their requests if the server closes the connection before sending all of the corresponding responses. Clients should not pipeline requests using non-idempotent methods or non-idempotent sequences of methods. See section 9.12. Otherwise, a premature termination of the transport connection could lead to indeterminate results. A client wishing to send a non-idempotent request should wait to send that request until it has received the response status for the previous request. 8.13 Proxy servers. It is especially important that proxies correctly implement the properties of the connection header field as specified in section 14.1. The proxy server must signal persistent connections separately with its clients and the origin servers or other proxy servers that it connects to. Each persistent connection applies to only one transport link. A proxy server must not establish a HTTP/1.1 persistent connection with an HTTP/1 client, but see RFC 2068-33 for information and discussion of the problems with the Keep Alive header implemented by many HTTP/1 clients. 8.14 Practical considerations. Servers usually have some timeout value beyond which they will no longer maintain an inactive connection. Proxy servers might make this a higher value, since it is likely that the client will be making more connections through the same server. The use of persistent connections places no requirements on the length or existence of this timeout for either the client or the server. When a client or server wishes to time out, it should issue a graceful close on the transport connection. Clients and servers should both constantly watch for the other side of the transport close and respond to it as appropriate. If a client or server does not detect the other side's close promptly, it could cause unnecessary resource drain on the network. A client, server, or proxy may close the transport connection at any time. For example, a client might have started to send a new request at the same time that the server has decided to close the idle connection. From the server's point of view, the connection is being closed while it was idle. But from the client's point of view, a request is in progress. Clients, servers, and proxies must be able to recover from asynchronous close events. Client software should reopen the transport connection and retransmit the aborted sequence of requests without user interaction, so long as the request sequence is idempotent C-section 912. Non-idempotent methods or sequences must not be automatically retried, although user agents may offer a human operator the choice of retraying the request S confirmation by user agent software with semantic understanding of the application may substitute for user confirmation. The automatic retry should not be repeated if the second sequence of requests fails. Servers should always respond to at least one request per connection. If at all possible, servers should not close a connection in the middle of transmitting a response unless a network or client failure is suspected. Clients that use persistent connections should limit the number of simultaneous connections that they maintain to a given server. A single user client should not maintain more than 2 connections with any server or proxy. A proxy should use up to 2 end connections to another server or proxy, where N is the number of simultaneously active users. These guidelines are intended to improve HTTP response times and avoid congestion. 82 message transmission requirements. 821 persistent connections and flow control. HTTP11 servers should maintain persistent connections and use TCP's flow control mechanisms to resolve temporary overloads rather than terminating connections with the expectation that clients will retry. The latter technique can exacerbate network congestion. 822. Monitoring connections for error status messages. An HTTP11 or later client sending a message body should monitor the network connection for an error status while it is transmitting the request. If the client sees an error status, it should immediately cease transmitting the body. If the body is being sent using a chunked encoding section 36, a zero-length chunk and empty trailer may be used to prematurely mark the end of the message. If the body was preceded by a content-length header, the client must close the connection. 823. Use of the 100 continue status. The purpose of the 100 continue status, see section 100 and 1, is to allow a client that is sending a request message with a request body to determine if the origin server is willing to accept the request based on the request headers. In some cases, it might either be inappropriate or highly inefficient for the client to send the body if the server will reject the message without looking at the body. Requirements for HTTP11 clients. If a client will wait for a 100 continue response before sending the request body, it must send an expect request header field section 1420 with the 100 continue expectation. A client must not send an expect request header field section 1420 with the 100 continue expectation if it does not intend to send a request body. Because of the presence of older implementations, the protocol allows ambiguous situations in which a client may send expect 100 continue without receiving either a 417 expectation failed status or a 100 continue status. Therefore, when a client sends this header field to an origin server, possibly via a proxy from which it has never seen a 100 continue status, the client should not wait for an indefinite period before sending the request body. Requirements for HTTP11 origin servers upon receiving a request, which includes an expect request header field with the 100 continue expectation. An origin server must either respond with 100 continue and continue to read from the input stream, or respond with a final status code. The origin server must not wait for the request body before sending the 100 continue response. If it responds with a final status code, it may close the transport connection, or it may continue to read and discard the rest of the request. It must not perform the requested method if it returns a final status code. An origin server should not send a 100 continue response if the request message does not include an expect request header field with the 100 continue expectation, and must not send a 100 continue response if such a request comes from an HTTP/1 or earlier client. There is an exception to this rule for compatibility with RFC 2068. A server may send a 100 continue status in response to an HTTP/1.1 PUT or post request that does not include an expect request header field with the 100 continue expectation. This exception applies only to HTTP/1.1 requests and not to requests with any other HTTP version value. An origin server may omit a 100 continue response if it has already received some or all of the request body for the corresponding request. An origin server that sends a 100 continue response must ultimately send a final status code once the request body is received and processed, unless it terminates the transport connection prematurely. If an origin server receives a request that does not include an expect request header field with the 100 continue expectation, the request includes a request body, and the server responds with a final status code before reading the entire request body from the transport connection. Then the server should not close the transport connection until it has read the entire request, or until the client closes the connection. Otherwise, the client might not reliably receive the response message. However, this requirement is not be construed as preventing a server from defending itself against denial of service attacks, or from badly broken client implementations requirements for HTTP/1.1 proxies. If a proxy receives a request that includes an expect request header field with the 100 continue expectation, and the proxy either knows that the next hop server complies with HTTP/1.1 or higher, or does not know the HTTP version of the next hop server, it must forward the request, including the expect header field, if the proxy knows that the version of the next hop server is HTTP/1 or lower. It must not forward the request must respond with a 417 expectation. Failed status proxies should maintain a cache recording the HTTP version, numbers received from recently referenced Nexthop servers. A proxy must not forward a 100 continue response if the request message was received from an HTTP/1 or earlier client and did not include an expect request header field with the 100 continue expectation. This requirement overrides the general rule for forwarding of 1 XX responses, see section 10.1. Client behavior. If server prematurely closes connection, if an HTTP/1.1 client sends a request which includes a request body, but which does not include an expect request header field with the 100 continue expectation, and if the client is not directly connected to an HTTP/1.1 origin server, and if the client sees the connection close before receiving any status from the server, the client SHOULD retry the request. If the client does retry this request, it may use the following binary exponential backoff algorithm to be assured of obtaining a reliable response. Initiate a new connection to the server, transmit the request headers. Initialize a variable R to the estimated round-trip time to the server, e.g., based on the time it took to establish the connection, or to a constant value of 5 seconds. If the round-trip time is not available, compute T equals R times 2 raised to the power N, where N is the number of previous retries of this request. Wait either for an error response from the server or for T seconds, whichever comes first. If no error response is received after T seconds, transmit the body of the request. If client sees that the connection is closed, prematurely repeat from step 1 until the request is accepted, an error response is received, or the user becomes impatient and terminates the retry process. If at any point an error status is received, the client should not continue and should close the connection if it has not completed sending the request message. 9 method definitions. The set of common methods for HTTP/1.1 is defined below. Although this set can be expanded, additional methods cannot be assumed to share the same semantics for separately extended clients and servers. The host request header field section 14.23 must accompany all HTTP/1.1 requests. 9.1 Safe and idempotent methods. 9.11 Safe methods implementors should be aware the software represents the user in their interactions over the internet and should be careful to allow the user to be aware of any actions they might take which may have an unexpected significance to themselves or others. In particular, the convention has been established that the GET and head methods should not have the significance of taking an action other than retrieval. These methods ought to be considered safe. This allows user agents to represent other methods, such as post, put, and delete, in a special way, so that the user is made aware of the fact that a possibly unsafe action is being requested. Naturally, it is not possible to ensure that the server does not generate side effects as a result of performing a GET request. In fact, some dynamic resources consider that a feature. The important distinction here is that the user did not request the side effects, so therefore cannot be held accountable for them. 9.12 Idempotent methods. Methods can also have the property of idempotence, in that aside from error or expiration, issues the side effects of N0 identical requests is the same as for a single request. The methods get, head, put, and delete share this property. Also, the methods options and trace SHOULD not have side effects, and so are inherently idempotent. However, it is possible that a sequence of several requests is non-idempotent, even if all of the methods executed in that sequence are idempotent. A sequence is non-idempotent if its result depends on a value that is later modified in the same sequence. A sequence that never has side effects is idempotent by definition, provided that no concurrent operations are being executed on the same set of resources. 9.2 Options. The options method represents a request for information about the communication options available on the request/response chain identified by the request URI. This method allows the client to determine the options and / or requirements associated with a resource, or the capabilities of a server without implying a resource action or initiating a resource retrieval. Responses to this method are not cacheable. If the options request includes an entity body, as indicated by the presence of content length or transferring coding, then the media type must be indicated by a content type field. Although this specification does not define any use for such a body, future extensions to HTTP might use the options body to make more detailed queries on the server. A server that does not support such an extension may discard the request body. If the request URI is an asterisk, the options request is intended to apply to the server in general rather than to a specific resource, since a server's communication options typically depend on the resource. The request is only useful as a ping or no-op type of method. It does nothing beyond allowing the client to test the capabilities of the server. For example, this can be used to test a proxy for HTTP/1.1 compliance or lack thereof. If the request URI is not an asterisk, the options request applies only to the options that are available when communicating with that resource. A 200 response, SHOULD, include any header fields that indicate optional features implemented by the server and applicable to that resource, e.g., allow, possibly including extensions not defined by this specification. The response body, if any, SHOULD, also include information about the communication options. The format for such a body is not defined by this specification, but might be defined by future extensions to HTTP. Content negotiation may be used to select the appropriate response format. If no response body is included, the response must include a content length field with a field value of 0. The max forwards request header field may be used to target a specific proxy in the request chain. When a proxy receives an options request on an absolute URI for which request forwarding is permitted, the proxy must check for a max forwards field. If the max forwards field value is 0, the proxy must not forward the message. Instead, the proxy should respond with its own communication options. If the max forwards field value is an integer greater than 0, the proxy must decrement the field value when it forwards the request. If no max forwards field is present in the request, then the forwarded request must not include a max forwards field. 9.3. Get the GET method means retrieve whatever information in the form of an entity is identified by the request URI. If the request URI refers to a data producing process, it is the produced data which shall be returned as the entity in the response, and not the source text of the process, unless that text happens to be the output of the process. The semantics of the GET method conditional GET. If the request message includes an if modified since, if unmodified since, if match, if none match, or if range header field, a conditional get method requests that the entity be transferred only under the circumstances described by the conditional header fields. The conditional GET method is intended to reduce unnecessary network usage by allowing cached entities to be refreshed without requiring multiple requests or transferring data already held by the client. The semantics of the GET method change to a partial GET if the request message includes a range header field. A partial get requests that only part of the entity be transferred, as described in section 14.35. The partial get method is intended to reduce unnecessary network usage by allowing partially retrieved entities to be completed without transferring data already held by the client. The response to a GET request is cacheable if and only if it meets the requirements for HTTP caching described in section 13. See section 15.13 for security considerations when used for forms. 9.4 head. The head method is identical to get, except that the server must not return a message body in the response. The meta information contained in the HTTP headers in response to a head request should be identical to the information sent in response to a GET request. This method can be used for obtaining meta information about the entity implied by the request without transferring the entity body itself. This method is often used for testing hypertext links for validity, accessibility, and recent modification. The response to a head request may be cacheable in the sense that the information contained in the response may be used to update a previously cached entity from that resource if the new field values indicate that the cached entity differs from the current entity, as would be indicated by a change in content length, contentemd5, etag, or last modified. Then the cache must treat the cache entry as stale. 9.5 post. The post method is used to request that the origin server accept the entity enclosed in the request as a new subordinate of the resource identified by the request URI in the request line. Post is designed to allow a uniform method to cover the following functions: annotation of existing resources, posting a message to a bulletin board, news group, mailing list, or similar group of articles providing a block of data, such as the result of submitting a form to a data handling process, extending a database through an append operation. The actual function performed by the post method is determined by the server and is usually dependent on the request URI. The posted entity is subordinate to that URI in the same way that a file is subordinate to a directory containing it. A news article is subordinate to a news group to which it is posted, or a record is subordinate to a database. The action performed by the post method might not result in a resource that can be identified by a URI. In this case, either 200 OK or 204 no content is the appropriate response status, depending on whether or not the response includes an entity that describes the result. If a resource has been created on the origin server, the response should be 201 created and contain an entity which describes the status of the request and refers to the new resource, and a location header C section 14.3. Responses to this method are not cacheable unless the response includes appropriate cache control or expires header fields. However, the 303 See Other response can be used to direct the user agent to retrieve a cacheable resource. Post requests must obey the message transmission requirements set out in section 8.2. See section 15.13 for security considerations. 9.6. Put the PUT method requests that the enclosed entity be stored under the supplied request URI. If the request URI refers to an already existing resource, the enclosed entity should be considered as a modified version of the one residing on the origin server. If the request URI does not point to an existing resource, and that URI is capable of being defined as a new resource by the requesting user agent, the origin server can create the resource with that URI. If a new resource is created, the origin server must inform the user agent via the 201 created response. If an existing resource is modified, either the 200 OK or 204 no content response codes should be sent to indicate successful completion of the request. If the resource could not be created or modified with the request URI, an appropriate error response should be given that reflects the nature of the problem. The recipient of the entity must not ignore any content, e.g., content train headers that it does not understand or implement, and must return a 501 not implemented response in such cases. If the request passes through a cache and the request URI identifies one or more currently cached entities, those entries should be treated as stale. Responses to this method are not cacheable. The fundamental difference between the POST and PUT requests is reflected in the different meaning of the request URI. The URI in a POST request identifies the resource that will handle the enclosed entity. That resource might be a data accepting process, a gateway to some other protocol, or a separate entity that accepts annotations. In contrast, the URI in a PUT request identifies the entity enclosed with the request. The user agent knows what URI is intended, and the server must not attempt to apply the request to some other resource if the server desires that the request be applied to a different URI. It must send a 301 moved permanently response. The user agent may then make its own decision regarding whether or not to redirect the request. A single resource may be identified by many different URIs. For example, an article might have a URI for identifying the current version, which is separate from the URI identifying each particular version. In this case, a PUT request on a general URI might result in several other URIs being defined by the origin server. HTTP/1.1 does not define how a PUT method affects the state of an origin server. PUT requests must obey the message transmission requirements set out in section 8.2. Unless otherwise specified for a particular entity header, the entity headers in the PUT request should be applied to the resource created or modified by the PUT. The delete method requests that the origin server delete the resource identified by the request URI. This method may be overridden by human intervention or other means on the origin server. The client cannot be guaranteed that the operation has been carried out, even if the status code returned from the origin server indicates that the action has been completed successfully. However, the server should not indicate success unless, at the time the response is given, it intends to delete the resource or move it to an inaccessible location. A successful response should be 200 OK. If the response includes an entity describing the status, 202 accepted. If the action has not yet been enacted, or 204 no content. If the action has been enacted, but the response does not include an entity, if the request passes through a cache and the request URI identifies one or more currently cached entities, those entries should be treated as stale. Responses to this method are not cacheable. 9.8 Trace. The trace method is used to invoke a remote application layer loopback of the request message. The final recipient of the request should reflect the message received back to the client as the entity body of a 200 OK response. The final recipient is either the origin server or the first proxy or gateway to receive a max forwards value of 0 in the request. A trace request must not include an entity. Trace allows the client to see what is being received at the other end of the request chain and use that data for testing or diagnostic information. The value of the via header field is of particular interest since it acts as a trace of the request chain. Use of the max forwards header field allows the client to limit the length of the request chain, which is useful for testing a chain of proxies forwarding messages in an infinite loop. If the request is valid, the response should contain the entire request message in the entity body with a content type of message/HTTP. Responses to this method must not be cached. 9.9 Connect. This specification reserves the method name connect for use with a proxy that can dynamically switch to being a tunnel, such as SSL tunneling. 10 Status code definitions. Each status code is described below, including a description of which methods it can follow and any meta information required in the response. 10.1 Informational 1 XX. This class of status code indicates a provisional response consisting only of the status line and optional headers and is terminated by an empty line. There are no required headers for this class of status code. Since HTTP/1 did not define any 1XX status codes, servers must not send a 1XX response to an HTTP/1 client except under experimental conditions. A client must be prepared to accept one or more 1XX status responses prior to a regular response, even if the client does not expect a 100 continue status message. Unexpected 1XX status responses may be ignored by a user agent. Proxies must forward 1XX responses unless the connection between the proxy and its client has been closed, or unless the proxy itself requested the generation of the 1XX response. For example, if a proxy adds an expect 100 continue field when it forwards a request, then it need not forward the corresponding 100 continue responses. 10.11100 continue. The client should continue with its request. This interim response is used to inform the client that the initial part of the request has been received and has not yet been rejected by the server. The client should continue by sending the remainder of the request, or if the request has already been completed, ignore this response. The server must send a final response after the request has been completed. See section 8.23 for detailed discussion of the use and handling of this status code. 10.12100 and 1. Switching protocols the server understands and is willing to comply with the client's request via the upgrade message header field. For a change in the application protocol being used on this connection, the server will switch protocols to those defined by the response's upgrade header field immediately after the empty line, which terminates the 100 and 1 response. The protocol should be switched only when it is advantageous to do so. For example, switching to a newer version of HTTP is advantageous over older versions, and switching to a real-time synchronous protocol might be advantageous when delivering resources that use such features. 10.2 Successful 2 XX. This class of status code indicates that the client's request was successfully received, understood, and accepted. 10.21200 OK. The request has succeeded. The information returned with the response is dependent on the method used in the request. For example, get an entity corresponding to the requested resource is sent in the response. Head the entity header fields corresponding to the requested resource are sent in the response without any message body. post an entity describing or containing the result of the action. Trace an entity containing the request message as received by the end server. 10.22200 and 1. Created the request has been fulfilled and resulted in a new resource being created. The newly created resource can be referenced by the URIs returned in the entity of the response, with the most specific URI for the resource given by a location header field. The response should include an entity containing a list of resource characteristics and locations from which the user or user agent can choose the one most appropriate. The entity format is specified by the media type given in the content type header field. The origin server must create the resource before returning the 201 status code. If the action cannot be carried out immediately, the server should respond with 202 accepted response instead. A 201 response may contain an ETAG response header field indicating the current value of the entity tag for the requested variant just created. See section 14.19, 10.23200 and 2. Accepted the request has been accepted for processing, but the processing has not been completed. The request might or might not eventually be acted upon, as it might be disallowed when processing actually takes place. There is no facility for resending a status code from an asynchronous operation such as this. The 202 response is intentionally non-committal. Its purpose is to allow a server to accept a request for some other process, perhaps a batch-oriented process that is only run once per day, without requiring that the user agent's connection to the server persist until the process is completed. The entity returned with this response should include an indication of the request's current status and either a pointer to a status monitor or some estimate of when the user can expect the request to be fulfilled. 10.24200 and 3. Non-authoritative information. The returned meta-information in the entity header is not the definitive set as available from the origin server, but is gathered from a local or a third-party copy. The set presented may be a subset or superset of the original version. For example, including local annotation information about the resource might result in a superset of the meta-information known by the origin server. Use of this response code is not required and is only appropriate when the response would otherwise be 200 OK. 10.25 200 and 4. No content. The server has fulfilled the request, but does not need to return an entity body and might want to return updated meta information. The response may include new or updated meta information in the form of entity headers, which, if present, should be associated with the requested variant. If the client is a user agent, it should not change its document view from that which caused the request to be sent. This response is primarily intended to allow input for actions to take place without causing a change to the user agent's active document view. Although any new or updated meta information should be applied to the document currently in the user agent's active view, the 204 response must not include a message body, and thus is always terminated by the first empty line after the header fields. 10.26 205 Reset content. The server has fulfilled the request, and the user agent SHOULD reset the document view which caused the request to be sent. This response is primarily intended to allow input for actions to take place via user input, followed by a clearing of the form in which the input is given, so that the user can easily initiate another input action. The response must not include an entity. 10.27 200 and 6. Partial content. The server has fulfilled the partial GET request for the resource. The request must have included a range header field, section 14.35, indicating the desired range, and may have included an if range header field, section 14.27, to make the request conditional. The response must include the following header fields: either a content range header field, section 14.16, indicating the range included with this response, or a multipart /byte ranges content type, including content range fields for each part. If a content length header field is present in the response, its value must match the actual number of octets transmitted in the message body, date, e-tag, and / or content location. If the header would have been sent in a 200 response to the same request, expires, cache control, and / or vary if the field value might differ from that sent in any previous response. For the same variant, if the 206 response is the result of an if-range request that used a strong cache validator. See section 13.33. The response should not include other entity headers if the response is the result of an if-range request that used a weak validator. The response must not include other entity headers. This prevents inconsistencies between cached entity bodies and updated headers. Otherwise, the response must include all of the entity headers that would have been returned with a 200 OK response to the same request. A cache must not combine a 206 response with other previously cached content if the E-tag or last modified headers do not match exactly. See 13.54. A cache that does not support the range and content range headers must not cache 206 partial responses. 10.3 Redirection 3 XX. This class of status code indicates that further action needs to be taken by the user agent in order to fulfill the request. The action required may be carried out by the user agent without interaction with the user, if and only if the method used in the second request is get or head. A client should detect infinite redirection loops, since such loops generate network traffic for each redirection. Note, previous versions of this specification recommended a maximum of 5 redirections. Content developers should be aware that there might be clients that implement such a fixed limitation. 10.31300 Multiple choices. The requested resource corresponds to any one of a set of representations, each with its own specific location, and agent-driven negotiation information, Section 12, is being provided so that the user or user agent can select a preferred representation and redirect its request to that location unless it was a head request. The response should include an entity containing a list of resource characteristics and locations from which the user or user agent can choose the one most appropriate. The entity format is specified by the media type given in the content type header field. Depending upon the format and the capabilities of the user agent, selection of the most appropriate choice may be performed automatically. However, this specification does not define any standard for such automatic selection. If the server has a preferred choice of representation, it should include the specific URI for that representation in the location field. User agents may use the location field value for automatic redirection. This response is cacheable unless indicated otherwise. 10.32300 and 1 moved permanently. The requested resource has been assigned a new permanent URI, and any future references to this resource should use one of the returned URIs. Clients with link editing capabilities ought to automatically relink references to the request URI to one or more of the new references returned by the server where possible. This response is cacheable unless indicated otherwise. The new permanent URI, SHOULD, be given by the location field in the response. Unless the request method was head, the entity of the response should contain a short hypertext note with a hyperlink to the new URIs. If the 301 status code is received in response to a request other than GET or HEAD, the user agent must not automatically redirect the request unless it can be confirmed by the user. Since this might change the conditions under which the request was issued, note, when automatically redirecting a post request after receiving a 301 status code, some existing HTTP/1 user agents will erroneously change it into a GET request. 10.33300 and 2 found the requested resource resides temporarily under a different URI. Since the redirection might be altered on occasion, the client should continue to use the request URI for future requests. This response is only cacheable if indicated by a cache control or expires header field. The temporary URI, SHOULD, be given by the location field in the response unless the request method was head. The entity of the response should contain a short hypertext note with a hyperlink to the new URIs. If the 302 status code is received in response to a request other than GET or HEAD, the user agent must not automatically redirect the request unless it can be confirmed by the user. Since this might change the conditions under which the request was issued, note RFC 1945 and RFC 2068 specify that the client is not allowed to change the method on the redirected request. However, most existing user agent implementations treat 302 as if it were a 303 response, performing a GET on the location field value regardless of the original request method. The status codes 303 and 307 have been added for servers that wish to make unambiguously clear which kind of reaction is expected of the client. 10.34300 and 3. See other. The response to the request can be found under a different URI, and SHOULD be retrieved using a GET method on that resource. This method exists primarily to allow the output of a post-activated script to redirect the user agent to a selected resource. The new URI is not a substitute reference for the originally requested resource. The 303 response must not be cached, but the response to the second redirected request might be cacheable. The different URI SHOULD be given by the location field in the response unless the request method was head. The entity of the response should contain a short hypertext note with a hyperlink to the new URIs. Note: many pre-HTTP/1.1 user agents do not understand the 303 status when interoperability with such clients is a concern. The 302 status code may be used instead. Since most user agents react to a 302 response, as described here for 303, 10.35300, and 4 not modified, if the client has performed a conditional GET request and access is allowed, but the document has not been modified, the server should respond with this status code. The 304 response must not contain a message body, and thus is always terminated by the first empty line after the header fields. The response must include the following header fields: date, unless its omission is required by section 14.181. If a clockless origin server obeys these rules, and proxies and clients add their own date to any response received without one, as already specified by RFC 2068, section 14.19. Caches will operate correctly, e-tag and slash, or content location. If the header would have been sent in a 200 response to the same request, expires, cache control, and slash or vary. If the field value might differ from that sent in any previous response for the same variant, if the conditional GET used a strong cache validator. See section 13.33. The response should not include other entity headers, otherwise i.e., the conditional GET used a weak validator. The response must not include other entity headers. This prevents inconsistencies between cached entity bodies and updated headers. If a 304 response indicates an entity not currently cached, then the cache must disregard the response and repeat the request without the conditional. If a cache uses a received 304 response to update a cache entry, the cache must update the entry to reflect any new field values given in the response. The requested resource must be accessed through the proxy given by the location field. The location field gives the URI of the proxy. The recipient is expected to repeat this single request via the proxy. 305 responses must only be generated by origin servers. Note: RFC 2068 was not clear that 305 was intended to redirect a single request and to be generated by origin servers only. Not observing these limitations has significant security consequences. The 306 status code was used in a previous version of the specification, is no longer used, and the code is reserved. The requested resource resides temporarily under a different URI. Since the redirection may be altered on occasion, the client should continue to use the request URI for future requests. This response is only cacheable if indicated by a cache control or expires header field. The temporary URI SHOULD be given by the location field in the response unless the request method was head. The entity of the response should contain a short hypertext note with a hyperlink to the new URIs. Since many pre-HTTP/1.1 user agents do not understand the 307 status, the note should contain the information necessary for a user to repeat the original request on the new URI. If the 307 status code is received in response to a request other than GET or HEAD, the user agent must not automatically redirect the request unless it can be confirmed by the user. Since this might change the conditions under which the request was issued, the 4XX class of status code is intended for cases in which the client seems to have erred, except when responding to a head request. The server should include an entity containing an explanation of the error situation and whether it is a temporary or permanent condition. These status codes are applicable to any request method. User agents should display any included entity to the user. If the client is sending data, a server implementation using TCP SHOULD. Be careful to ensure that the client acknowledges receipt of the packets containing the response before the server closes the input connection. If the client continues sending data to the server after the close, the server's TCP stack will send a reset packet to the client, which may erase the client's unacknowledged input buffers before they can be read and interpreted by the HTTP application. The request could not be understood by the server due to malformed syntax. The client should not repeat the request without modifications. The request requires user authentication. The response must include a www authenticate header field containing a challenge applicable to the requested resource. The client may repeat the request with a suitable authorization header field if the request already included authorization credentials. Then the 401 response indicates that authorization has been refused for those credentials. If the 401 response contains the same challenge as the prior response, and the user agent has already attempted authentication at least once, then the user should be presented the entity that was given in the response, since that entity might include relevant diagnostic information. HTTP access authentication is explained in HTTP authentication, basic and digest access authentication. This code is reserved for future use. The server understood the request, but is refusing to fulfill it. Authorization will not help, and the request should not be repeated. If the request method was not head, and the server wishes to make public why the request has not been fulfilled, it should describe the reason for the refusal in the entity. If the server does not wish to make this information available to the client, the status code 404, not found, can be used instead. The requested resource could not be found on the server. The server has not found anything matching the request URI. No indication is given of whether the condition is temporary or permanent. The 410 gone status code should be used if the server knows, through some internally configurable mechanism, that an old resource is permanently unavailable and has no forwarding address. This status code is commonly used when the server does not wish to reveal exactly why the request has been refused, or when no other response is applicable. 10.46405 method, not allowed the method specified in the request line, is not allowed for the resource identified by the request URI. The response must include an allow header containing a list of valid methods for the requested resource. 10.47406, not acceptable. The resource identified by the request is only capable of generating response entities which have content characteristics not acceptable according to the accept headers sent in the request, unless it was a head request. The response should include an entity containing a list of available entity characteristics and locations from which the user or user agent can choose the one most appropriate. The entity format is specified by the media type given in the content type header field. Depending upon the format and the capabilities of the user agent, selection of the most appropriate choice may be performed automatically. However, this specification does not define any standard for such automatic selection. Note: HTTP/1.1 servers are allowed to return responses which are not acceptable according to the accept headers sent in the request. In some cases, this may even be preferable to sending a 406 response. User agents are encouraged to inspect the headers of an incoming response to determine if it is acceptable. If the response could be unacceptable, a user agent SHOULD temporarily stop receipt of more data and query the user for a decision on further actions. 10.48407 proxy authentication required. This code is similar to 401 unauthorized, but indicates that the client must first authenticate itself with the proxy. The proxy must return a proxy authenticate header field containing a challenge applicable to the proxy for the requested resource. The client may repeat the request with a suitable proxy authorization header field. HTTP access authentication is explained in HTTP authentication. Basic and digest access authentication. 43. 10.49400 and 8 request timeout. The client did not produce a request within the time that the server was prepared to wait. The client may repeat the request without modifications at any later time. 10.49401 10.410.400. And 9. Conflict. The request could not be completed due to a conflict with the current state of the resource. This code is only allowed in situations where it is expected that the user might be able to resolve the conflict and resubmit the request. The response body, SHOULD, include enough information for the user to recognize the source of the conflict. Ideally, the response entity would include enough information for the user or user agent to fix the problem. However, that might not be possible and is not required. Conflicts are most likely to occur in response to a put request. For example, if versioning were being used and the entity being put included changes to a resource which conflict with those made by an earlier third-party request, the server might use the 409 response to indicate that it can't complete the request. In this case, the response entity would likely contain a list of the differences between the two versions in a format defined by the response content type. 10.411.400 and 10. Gone. The requested resource is no longer available at the server, and no forwarding address is known. This condition is expected to be considered permanent. Clients with link editing capabilities should delete references to the request URI after user approval. If the server does not know or has no facility to determine whether or not the condition is permanent, the status code 404, not found, should be used instead. This response is cacheable unless indicated otherwise. The 410 response is primarily intended to assist the task of web maintenance by notifying the recipient that the resource is intentionally unavailable and that the server owner's desire that remote links to that resource be removed. Such an event is common for limited time promotional services and for resources belonging to individuals no longer working at the server's site. It is not necessary to mark all permanently unavailable resources as gone, or to keep the mark for any length of time. That is left to the discretion of the server owner. 10.412.400 and 11 length required the server refuses to accept the request without a defined content length. The client may repeat the request if it adds a valid content length header field containing the length of the message body in the request message. 10.413.400 and 12. Precondition. failed the precondition given in one or more of the request header fields, evaluated to false when it was tested on the server. This response code allows the client to place preconditions on the current resource meta information, header field data, and thus prevent the requested method from being applied to a resource other than the one intended. 10.414.400 and 13 request entity. 2. Large. The server is refusing to process a request because the request entity is larger than the server is willing or able to process. The server may close the connection to prevent the client from continuing the request. If the condition is temporary, the server should include a retry after header field to indicate that it is temporary, and after what time the client may try again. 10.415.400 and 14 request URI. Too long. The server is refusing to service the request because the request URI is longer than the server is willing to interpret. This rare condition is only likely to occur when a client has improperly converted a POST request to a GET request with long query information, when the client has descended into a URI black hole of redirection, e.g., a redirected URI prefix that points to a suffix of itself, or when the server is under attack by a client attempting to exploit security holes present in some servers, using fixed-length buffers for reading or manipulating the request URI. 10.416.400 and 15 unsupported media type. The server is refusing to service the request because the entity of the request is in a format not supported by the requested resource for the requested method. 10.417.400 and 16 requested range not satisfiable. A server should return a response with this status code if a request included a range request header field. Section 14.35 and none of the range specifier values in this field overlap the current extent of the selected resource, and the request did not include an if range request header field for byte ranges. This means that the first byte pose of all of the byte range spec values were greater than the current length of the selected resource. When this status code is returned for a byte range request, the response should include a content range entity header field specifying the current length of the selected resource. See section 14.16 This response must not use the multipart / byte ranges content type. 10.418.400 and 17. Expectation. Failed the expectation given in an expect request header field. See section 14.2. Could not be met by this server. Or if the server is a proxy, the server has unambiguous evidence that the request could not be met by the next hop server. 10.5 Server error 5 XX response status codes beginning with the digit 5 indicate cases in which the server is aware that it has erred or is incapable of performing the request except when responding to a head request. The server should include an entity containing an explanation of the error situation and whether it is a temporary or permanent condition. User agents should display any included entity to the user. These response codes are applicable to any request method. 10.51500 Internal server error. The server encountered an unexpected condition which prevented it from fulfilling the request. 10.52500 and one not implemented. The server does not support the functionality required to fulfill the request. This is the appropriate response when the server does not recognize the request method and is not capable of supporting it for any resource. 10.53500 and 2. Bad gateway the server while acting as a gateway or proxy received an invalid response from the upstream server it accessed in attempting to fulfill the request. 10.54500 and 3. Service unavailable. The server is currently unable to handle the request due to a temporary overloading or maintenance of the server. The implication is that this is a temporary condition which will be alleviated after some delay. If known, the length of the delay may be indicated in a retry after header. If no retry after is given, the client should handle the response as it would for a 500 response. Note, the existence of the 503 status code does not imply that a server must use it when becoming overloaded. Some servers may wish to simply refuse the connection. 10.55504 Gateway timeout the server while acting as a gateway or proxy did not receive a timely response from the upstream server specified by the URI, e.g., HTTP, FTP, LDAP, or some other auxiliary server, e.g. DNS, it needed to access in attempting to complete the request. Note to implementors. Some deployed proxies are known to return 400 or 500 when DNS lookups time out. 10.56 500 and 5 HTTP version not supported. The server does not support or refuses to support the HTTP protocol version that was used in the request message. The server is indicating that it is unable or unwilling to complete the request using the same major version as the client, as described in section 3.1. Other than with this error message, the response should contain an entity describing why that version is not supported and what other protocols are supported by that server. 11. Access Authentication HTTP provides several optional challenge response authentication mechanisms which can be used by a server to challenge a client request and by a client to provide authentication information. The general framework for access authentication and the specification of basic and digest authentication are specified in HTTP authentication. Basic and digest access authentication. This specification adopts the definitions of challenge and credentials from that specification. 12. Content negotiation. Most HTTP responses include an entity which contains information for interpretation by a human user. Naturally, it is desirable to supply the user with the best available entity corresponding to the request. Unfortunately for servers and caches, not all users have the same preferences for what is best, and not all user agents are equally capable of rendering all entity types. For that reason, HTTP has provisions for several mechanisms for content negotiation. The process of selecting the best representation for a given response when there are multiple representations available. Note, this is not called format negotiation because the alternate representations may be of the same media type but use different capabilities of that type, be in different languages, etc. Any response containing an entity body may be subject to negotiation, including error responses. There are two kinds of content negotiation which are possible in HTTP: server-driven and agent-driven negotiation. These two kinds of negotiation are orthogonal and thus may be used separately or in combination. One method of combination, referred to as transparent negotiation, occurs when a cache uses the agent-driven negotiation information provided by the origin server in order to provide server-driven negotiation for subsequent requests. Server-driven negotiation is advantageous when the algorithm for selecting from among the available representations is difficult to describe to the user agent, or when the server desires to send its best guess to the client, along with the first response, hoping to avoid round-trip delay of a subsequent request if the best guess is good enough for the user. In order to improve the server's guess, the user agent may include request header fields such as accept language, accept encoding, which describe its preferences for such a response. Server-driven negotiation has disadvantages. It is impossible for the server to accurately determine what might be best for any given user, since that would require complete knowledge of both the capabilities of the user agent and the intended use for the response, e.g., does the user want to view it on screen or print it on paper? Having the user agent describe its capabilities in every request can be both very inefficient, given only a small percentage of responses have multiple representations, and a potential violation of the user's privacy. It complicates the implementation of an origin server and the algorithms for generating responses to a request. It may limit a public cache's ability to use the same response for multiple users' requests. HTTP/1.1 includes the following request header fields for enabling server-driven negotiation through description of user agent capabilities and user preferences, accept charset, accept encoding, accept language, and user agent. However, an origin server is not limited to these dimensions and may vary the response based on any aspect of the request, including information outside the request header fields or within extension header fields not defined by this specification. The very header field can be used to express the parameters the server uses to select a representation that is subject to server-driven negotiation. See Section 13.6 for use of the very header field by caches, and Section 14 1.44 for use of the very header field by servers with agent-driven negotiation selection of the best representation for a response is performed by the user agent after receiving an initial response from the origin server. Selection is based on a list of available representations of the response included within the header fields or entity body of the initial response, with each representation identified by its own URI. Selection from among the representations may be performed automatically if the user agent is capable of doing so, or manually by the user selecting from a generated, possibly hypertext menu. Agent-driven negotiation is advantageous when the response would vary over commonly used dimensions, such as type language, or encoding when the origin server is unable to determine a user agent's capabilities from examining the request, and generally when public caches are used to distribute server load and reduce network usage. Agent-driven negotiation suffers from the disadvantage of needing a second request to obtain the best alternate representation. This second request is only efficient when caching is used. In addition, this specification does not define any mechanism for supporting automatic selection, though it also does not prevent any such mechanism from being developed as an extension and used within HTTP/1.1. HTTP/1.1 defines the 300 multiple choices and 406 not acceptable status codes for enabling agent-driven negotiation when the server is unwilling or unable to provide a varying response using server-driven negotiation. Transparent negotiation is a combination of both server-driven and agent-driven negotiation. When a cache is supplied with a form of the list of available representations of the response, as in agent-driven negotiation, and the dimensions of variance are completely understood by the cache, then the cache becomes capable of performing server-driven negotiation on behalf of the origin server for subsequent requests on that resource. Transparent negotiation can distribute the negotiation work otherwise required by the origin server and remove the second request delay in agent-driven negotiation when the cache correctly guesses the right response. This specification does not define any mechanism for transparent negotiation, but also does not prevent such a mechanism from being developed as an extension within HTTP/1.1. Caching is used to improve performance in distributed information systems by using response caches. The HTTP/1.1 protocol includes elements intended to make caching work effectively, which are intertwined with other aspects of the protocol and interact with each other. Therefore, it is useful to describe the basic caching design of HTTP separately from detailed descriptions of methods, headers, response codes, etc. Caching would be ineffective if it did not significantly improve performance. The goal of caching in HTTP/1.1 is to eliminate the need to send requests in many cases and reduce the need to send full responses in other cases. Sending fewer requests reduces network round trips for operations. An expiration mechanism is used for this. See section 13.2. Reducing response size decreases network bandwidth requirements. A validation mechanism is used for this. See section 13.3. Performance, availability, and disconnected operation goals require the ability to relax semantic transparency. The HTTP/1.1 protocol allows origin servers, caches, and clients to explicitly reduce transparency when necessary. Non-transparent operation might confuse non-expert users or be incompatible with certain server applications, such as those for ordering merchandise. Therefore, the protocol requires that transparency be relaxed only by an explicit protocol-level request from a client or origin server. Only with an explicit warning to the end user. If relaxed by a cache or client, the HTTP/1.1 protocol provides these elements. Protocol features providing full semantic transparency when required by all parties. Protocol features allowing an origin server or user agent to explicitly request and control non-transparent operation. Protocol features allowing a cache to attach warnings to responses that do not preserve the requested approximation of semantic transparency. Clients must be able to detect any potential relaxation of semantic transparency. Note, if a design decision might affect semantic transparency, implementors should favor maintaining transparency unless careful analysis shows significant benefits in breaking it. A correct cache must respond to a request with the most up-to-date response held by the cache that is appropriate to the request. This response meets one of these conditions. It has been checked for equivalence with what the origin server would have returned by revalidating the response with the origin server. See section 13.3. It is fresh enough. See section 13.2. In default cases, it must meet the least restrictive freshness requirement of the client, origin server, and cache. See section 14.9. If the origin server specifies, it follows its own freshness requirement alone. If a stored response is not fresh enough, by the most restrictive freshness requirement of both the client and the origin server, in carefully considered circumstances, the cache may still return the response with the appropriate warning header. See section 13.15 and 14.46. Unless such a response is prohibited, e.g., by a no-store cache directive or by a no-cache cache request directive, see section 14.9. It is an appropriate 304, not modified, 305 proxy redirect, or error 4XX or 5XX response message if the cache cannot communicate with the origin server. Then a correct cache should respond as above if the response can be correctly served from the cache. If not, it must return an error or warning indicating that there was a communication failure. If a cache receives a response, either an entire response or a 304 not modified response, that it would normally forward to the requesting client, and the received response is no longer fresh, the cache should forward it to the requesting client without adding a new warning, but without removing any existing warning headers. A cache should not attempt to revalidate a response simply because that response became stale in transit. This might lead to an infinite loop. A user agent that receives a stale response without a warning may display a warning indication to the user whenever a cache returns a response that is neither first-hand nor fresh enough. In the sense of condition 2 in section 13.11, it must attach a warning to that effect using a warning general header. The warning header and the currently defined warnings are described in section 14.46. The warning allows clients take appropriate action. Warnings may be used for other purposes, both cache-related and otherwise. The use of a warning, rather than an error status code, distinguish these responses from true failures. Warnings are assigned 3-digit warn codes. The first digit indicates whether the warning must or must not be deleted from a stored cache entry after a successful revalidation. 1XX warnings that describe the freshness or revalidation status of the response, and so must be deleted after a successful revalidation. 1XX warn codes may be generated by a cache only when validating a cached entry. It must not be generated by clients. 2XX warnings that describe some aspect of the entity body or entity headers that is not rectified by a revalidation. For example, a lossy compression of the entity bodies, and which must not be deleted after a successful revalidation. See section 14.46 for the definitions of the codes themselves. HTTP/1 caches will cache all warnings in responses without deleting the ones in the first category. Warnings in responses that are passed to HTTP/1 caches carry an extra warning date field, which prevents a future HTTP/1.1 recipient from believing an erroneously cached warning. Warnings also carry a warning text. The text may be in any appropriate natural language, perhaps based on the client's accept headers, and include an optional indication of what character set is used. Multiple warnings may be attached to a response, either by the origin server or by a cache, including multiple warnings with the same code number. For example, a server might provide the same warning with texts in both English and Basque. When multiple warnings are attached to a response, it might not be practical or reasonable to display all of them to the user. This version of HTTP does not specify strict priority rules for deciding which warnings to display and in what order, but does suggest some heuristics. The cache control header allows a client or server to transmit a variety of directives in either requests or responses. These directives typically override the default caching algorithms. As a general rule, if there is any apparent conflict between header values, the most restrictive interpretation is applied that is most likely to preserve semantic transparency. However, in some cases, cache control directives are explicitly specified as weakening the approximation of semantic transparency. For example, max stale or public. The cache control directives are described in detail in section 14.9. 13.14 Explicit user agent warnings. Many user agents make it possible for users to override the basic caching mechanisms. For example, the user agent might allow the user to specify that cached entities, even explicitly stale ones, are never validated. Or the user agent might habitually add cache control max stale equals 36.0 to every request. The user agent should not default to either non-transparent behavior or behavior that results in abnormally ineffective caching, but may be explicitly configured to do so by an explicit action of the user if the user has overridden the basic caching mechanisms. The user agent SHOULD explicitly indicate to the user whenever this results in the display of information that might not meet the server's transparency requirements, in particular if the displayed entity is known to be stale, since the protocol normally allows the user agent to determine if responses are stale or not. This indication need only be displayed when this actually happens. The indication need not be a dialog box. It could be an icon, for example, a picture of a rotting fish, or some other indicator if the user has overridden the caching mechanisms in a way that would abnormally reduce the effectiveness of caches. The user agent should continually indicate this state to the user, for example, by a display of a picture of currency in flames, so that the user does not inadvertently consume excess resources or suffer from excessive latency. 13.15 Exceptions to the rules and warnings. In some cases, the operator of a cache may choose to configure it to return stale responses, even when not requested by clients. This decision ought not be made lightly, but may be necessary for reasons of availability or performance, especially when the cache is poorly connected to the origin server. Whenever a cache returns a stale response, it must mark it as such using a warning header, enabling the client software to alert the user that there might be a potential problem. It also allows the user agent to take steps to obtain a first-hand or fresh response. For this reason, a cache should not return a stale response if the client explicitly requests a first-hand or fresh one, unless it is impossible to comply for technical or policy reasons. 13.16 Client-controlled behavior, while the origin server, and to a lesser extent intermediate caches, by their contribution to the age of a response, are the primary source of expiration information. In some cases, the client might need to control a cache's decision about whether to return a cached response without validating it. Clients do this using several directives of the cache control header. A client's request may specify the maximum age it is willing to accept of an unvalidated response. Specifying a value of 0 forces the caches to revalidate all responses. A client may also specify the minimum time remaining before a response expires. Both of these options increase constraints on the behavior of caches, and so cannot further relax the cache's approximation of semantic transparency. A client may also specify that it will accept stale responses up to some maximum amount of staleness. This loosens the constraints on the caches, and so might violate the origin server's specified constraints on semantic transparency, but might be necessary to support disconnected operation or high availability in the face of poor connectivity. 13.2 Expiration Model. 13.21 Server-specified expiration. HTTP caching works best when caches can entirely avoid making requests to the origin server. The primary mechanism for avoiding requests is for an origin server to provide an explicit expiration time in the future, indicating that a response may be used to satisfy subsequent requests. In other words, a cache can return a fresh response without first contacting the server. Our expectation is that servers will assign future explicit expiration times to responses in the belief that the entity is not likely to change in a semantically significant way before the expiration time is reached. This normally preserves semantic transparency as long as the server's expiration times are carefully chosen. The expiration mechanism applies only to responses taken from a cache and not to first-hand responses forwarded immediately to the requesting client. If an origin server wishes to force a semantically transparent cache to validate every request, it may assign an explicit expiration time in the past. This means that the response is always stale, and so the cache should validate it before using it for subsequent requests. See section 14.94 for a more restrictive way to force revalidation. If an origin server wishes to force any HTTP/1.1 cache, no matter how it is configured, to validate every request, it should use the must-revalidate cache control directive, see section 14.9. Servers specify explicit expiration times using either the expires header or the max age directive of the cache control header. An expiration time cannot be used to force a user agent to refresh its display or reload a resource. Its semantics apply only to caching mechanisms, and such mechanisms need only check a resource's expiration status when a new request for that resource is initiated. See section 13.13 for an explanation of the difference between caches and history mechanisms. Since origin servers do not always provide explicit expiration times, HTTP caches typically assign heuristic expiration times, employing algorithms that use other header values, such as the last modified time, to estimate a plausible expiration time. The HTTP/1.1 specification does not provide specific algorithms, but does impose worst-case constraints on their results. Since heuristic expiration times might compromise semantic transparency, they ought to be used cautiously, and we encourage origin servers to provide explicit expiration times as much as possible. In order to know if a cached entry is fresh, a cache needs to know if its age exceeds its freshness lifetime. We discuss how to calculate the latter in section 13.24. This section describes how to calculate the age of a response or cache entry. In this discussion, we use the term now to mean the current value of the clock at the host performing the calculation. Hosts that use HTTP, especially hosts running origin servers and caches, should use NTP or some similar protocol to synchronize their clocks to a globally accurate time standard. HTTP/1.1 1.1 requires origin servers to send a date header, if possible, with every response, giving the time at which the response was generated. See section 14.18. We use the term date value to denote the value of the date header in a form appropriate for arithmetic operations. HTTP/1.1 uses the age response header to convey the estimated age of the response message when obtained from a cache. The age field value is the cache's estimate of the amount of time since the response was generated or revalidated by the origin server. In essence, the age value is the sum of the time that the response has been resident in each of the caches along the path from the origin server, plus the amount of time it has been in transit along network paths. We use the term age value to denote the value of the age header in a form appropriate for arithmetic operations. A response's age can be calculated in two entirely independent ways. 1. Now minus date value. If the local clock is reasonably well synchronized to the origin server's clock, if the result is negative, the result is replaced by 0. 2. Age value. If all of the caches along the response path implement HTTP/1.1, given that we have two independent ways to compute the age of a response when it is received, we can combine these as corrected received age equals max. Now date value, age value. And as long as we have either nearly synchronized clocks or all HTTP/1.1 paths, one gets a reliable, conservative result because of network-imposed delays. Some significant interval might pass between the time that a server generates a response and the time it is received at the next outbound cache or client. If uncorrected, this delay could result in improperly low ages. Because the request that resulted in the returned age value must have been initiated prior to that age value's generation, we can correct for delays imposed by the network by recording the time at which the request was initiated. Then, when an age value is received, it must be interpreted relative to the time the request was initiated, not the time that the response was received. This algorithm results in conservative behavior no matter how much delay is experienced. So we compute corrected initial age equals corrected received age plus. Now request time, where request time is the local time when the request that elicited this response was sent. Summary of age calculation algorithm. When a cache receives a response, /age value is the value of age. Header received by the cache with this response. Date value is the value of the origin server's date. Header request time is the local time when the cache made the request that resulted in this cached response time is the local time when the cache received the response now is the current local time / apparent age equals max 0. Response time date value corrected received age equals max apparent age value. Response delay equals response time. Request time corrected initial age equals corrected received age plus response delay. Resident time equals now response time. Current age equals corrected initial age plus resident time. The current age of a cache entry is calculated by adding the amount of time in seconds. Since the cache entry was last validated by the origin server to the corrected initial age when a response is generated from a cache entry, the cache must include a single age header field in the response with a value equal to the cache entry's current age. The presence of an age header field in a response implies that a response is not firsthand. However, the converse is not true, since the lack of an age header field in a response does not imply that the response is firsthand unless all caches along the request path are compliant with HTTP/1.1 IE. Older HTTP caches did not implement the age header field in order to decide whether a response is fresh or stale. We need to compare its freshness lifetime to its age. The age is calculated as described in section 13.23. This section describes how to calculate the freshness lifetime and to determine if a response has expired. In the discussion below, the values can be represented in any form appropriate for arithmetic operations. We use the term expires value to denote the value of the expires header. We use the term max age value to denote an appropriate value of the number of seconds carried by the max age directive of the cache control header in a response. See section 14.93. The max age directive takes priority over expires. So if max age is present in a response, the calculation is simply freshness lifetime equals max age value otherwise. If expires is present in the response, the calculation is freshness lifetime equals expires value date value. Note that neither of these calculations is vulnerable to clock skew, since all of the information comes from the origin server. If none of expires, cache control, max age, or cache control, S-maxage appears in the response, and the response does not include other restrictions on caching. The cache may compute a freshness lifetime using a heuristic. The cache must attach warning 113 to any response whose age is more than 24 hours if such warning has not already been added. Also, if the response does have a last modified time, the heuristic expiration value should be no more than some fraction of the interval since that time. A typical setting of this fraction might be 10%. The calculation to determine if a response has expired is quite simple. Response is fresh equals freshness lifetime current age. Because expiration values are assigned optimistically, it is possible for two caches to contain fresh values for the same resource that are different. If a client performing a retrieval receives a non-first-hand response for a request that was already fresh in its own cache, and the date header in its existing cache entry is newer than the date on the new response, then the client may ignore the response. If so, it may retry the request with a cache control. Max age equals 0, directive C section 14.9. To force a check with the origin server if a cache has two fresh responses for the same representation with different validators, it must use the one with the more recent date header. This situation might arise because the cache is pooling responses from other caches, or because a client has asked for a reload or a revalidation of an apparently fresh cache entry. Because a client might be receiving responses via multiple paths, so that some responses flow through one set of caches and other responses flow through a different set of caches. A client might receive responses in an order different from that in which the origin server sent them. We would like the client to use the most recently generated response, even if older responses are still apparently fresh. Neither the entity tag nor the expiration value can impose an ordering on responses, since it is possible that a later response intentionally carries an earlier expiration time. The date values are ordered to a granularity of 1 second. When a client tries to revalidate a cache entry and the response it receives contains a date header that appears to be older than the one for the existing entry, then the client should repeat the request unconditionally and include cache control max age equals 0 to force any intermediate caches to validate their copies directly with the origin server, or cache control no cache to force any intermediate caches to obtain a new copy from the origin server. If the date values are equal, then the client may use either response, or may, if it is being extremely prudent, request a new response. Servers must not depend on clients being able to choose deterministically between responses generated during the same second if their expiration times overlap. When a cache has a stale entry that it would like to use as a response to a client's request, it first has to check with the origin server, or possibly an intermediate cache with a fresh response, to see if its cached entry is still usable. We call this validating the cache entry. Since we do not want to have to pay the overhead of retransmitting the full response if the cached entry is good, and we do not want to pay the overhead of an extra round trip if the cached entry is invalid, the HTTP/1.1 protocol supports the use of conditional methods. The key protocol features for supporting conditional methods are those concerned with cache validators. When an origin server generates a full response, it attaches some sort of validator to it, which is kept with the cache entry when a client, user agent, or proxy cache makes a conditional request for a resource for which it has a cache entry. It includes the associated validator in the request. The server then checks that validator against the current validator for the entity, and if they match, see section 13.33. It responds with a special status code, usually 304, not modified, and no entity body. Otherwise, it returns a full response, including entity body. Thus, we avoid transmitting the full response if the validator matches, and we avoid an extra round trip if it does not match. In HTTP/1.1, a conditional request looks exactly the same as a normal request for the same resource, except that it carries a special header, which includes the validator that implicitly turns the method, usually GET, into a conditional. The protocol includes both positive and negative senses of cache validating conditions. That is, it is possible to request either that a method be performed if and only if a validator matches, or if and only if no validators match. Note, a response that lacks a validator may still be cached and served from cache until it expires, unless this is explicitly prohibited by a cache control directive. However, a cache cannot do a conditional retrieval if it does not have a validator for the entity, which means it will not be refreshable after it expires. 13.31 Last modified dates. The last modified entity header field value is often used as a cache validator. In simple terms, a cache entry is considered to be valid if the entity has not been modified since the last modified value. 13.32 Entity tag cache validators the e-tag response header field value. An entity tag provides for an opaque cache validator. This might allow more reliable validation in situations where it is inconvenient to store modification dates, where the 1-second resolution of HTTP date values is not sufficient, or where the origin server wishes to avoid certain paradoxes that might arise from the use of modification dates. Entity tags are described in section 3.11. The headers used with entity tags are described in sections 14.19, 14.24, 14.26, and 14.44, 13.33 weak and strong validators. Since both origin servers and caches will compare two validators to decide if they represent the same or different entities, one normally would expect that if the entity body, or any entity headers changes in any way, then the associated validator would change as well. If this is true, then we call this validator a strong validator. However, there might be cases when a server prefers to change the validator only on semantically significant changes, and not when insignificant aspects of the entity change. A validator that does not always change when the resource changes is a weak validator. Entity tags are normally strong validators, but the protocol provides a mechanism to tag an entity tag as weak. One can think of a strong validator as one that changes whenever the bits of an entity changes, while a weak value changes whenever the meaning of an entity changes. Alternatively, one can think of a strong validator as part of an identifier for a specific entity, while a weak validator is part of an identifier for a set of semantically equivalent entities. Note, one example of a strong validator is an integer that is incremented in stable storage every time an entity is changed. An entity's modification time, if represented with 1 second resolution, could be a weak validator, since it is possible that the resource might be modified twice during a single second. Support for weak validators is optional. However, weak validators allow for more efficient caching of equivalent objects. For example, a hit counter on a site is probably good enough if it is updated every few days or weeks, and any value during that period is likely good enough to be equivalent. A use of a validator is either when a client generates a request and includes the validator in a validating header field, or when a server compares two validators. Strong validators are usable in any context. Weak validators are only usable in contexts that do not depend on exact equality of an entity. For example, either kind is usable for a conditional get of a full entity. However, only a strong validator is usable for a subrange retrieval, since otherwise the client might end up with an internally inconsistent entity. Clients may issue simple, non-subrange get requests with either weak validators or strong validators. Clients must not use weak validators in other forms of request. The only function that the HTTP/1.1 protocol defines on validators is comparison. There are two validator comparison functions, depending on whether the comparison context allows the use of weak validators or not. The strong comparison function. In order to be considered equal, both validators must be identical in every way, and both must not be weak. The weak comparison function. In order to be considered equal, both validators must be identical in every way, but either or both of them may be tagged as weak without affecting the result. An entity tag is strong unless it is explicitly tagged as weak. Section 3.1 gives the syntax for entity tags. A last modified time, when used as a validator in a request, is implicitly weak unless it is possible to deduce that it is strong. Using the following rules, the validator is being compared by an origin server to the actual current validator for the entity. And that origin server reliably knows that the associated entity did not change twice during the second covered by the presented validator, or the validator is about to be used by a client in an if modified since or if unmodified since header, because the client has a cache entry for the associated entity. That cache entry includes a date value, which gives the time when the origin server sent the original response. The presented last modified time is at least 60 seconds before the date value, or the validator is being compared by an intermediate cache to the validator stored in its cache entry for the entity. That cache entry includes a date value, which gives the time when the origin server sent the original response. The presented last modified time is at least 60 seconds before the date value. This method relies on the fact that if two different responses were sent by the origin server during the same second, but both had the same last modified time, then at least one of those responses would have a date value equal to its last modified time. The arbitrary 60-second limit guards against the possibility that the date and last modified values are generated from different clocks or at somewhat different times during the preparation of the response. An implementation may use a value larger than 60 seconds if it is believed that 60 seconds is too short. If a client wishes to perform a sub-range retrieval on a value for which it has only a last modified time and no opaque validator, it may do this only if the last modified time is strong in the sense described here. A cache or origin server receiving a conditional request other than a full-body GET request must use the strong comparison function to evaluate the condition. These rules allow HTTP/1.1 caches and clients to safely perform sub-range retrievals on values that have been obtained from HTTP/1 servers. We adopt a set of rules and recommendations for origin servers, clients, and caches regarding when various validator types ought to be used and for what purposes. HTTP/1.1 origin servers, SHOULD, send an entity tag validator unless it is not feasible to generate one. May send a weak entity tag instead of a strong entity tag if performance considerations support the use of weak entity tags, or if it is unfeasible to send a strong entity tag. When sending a last modified value, it is advisable to do so unless the risk of a breakdown in semantic transparency due to its use in an if modified since header would cause serious problems. In other words, HTTP/1.1 origin servers are recommended to send both a strong entity tag and a last modified value as preferred behavior. A strong entity tag must change whenever any part of the associated entity changes. A weak entity tag should change when there is a semantically significant change in the associated entity. Note, to ensure semantically transparent caching, an origin server must not reuse a specific strong entity tag for different entities, or a specific weak entity tag for semantically different entities. Cache entries could persist indefinitely regardless of expiration times. So, it might be inappropriate to expect that a cache will never again attempt to validate using a validator obtained in the past. HTTP/1.1 clients are instructed as follows. If an entity tag is provided by the origin server, use it in any cache conditional request using if match or if none match if only a last modified value has been given. Use that value in non-subrange cache conditional requests using if modified since. If only a last modified value was provided by an HTTP/1 origin server, it may be used in subrange cache conditional requests using if unmodified since. The user agent should provide a way to disable this option if needed. When both an entity tag and a last modified value have been provided by the origin server, use both validators in cache conditional requests. This allows HTTP/1 and HTTP/1.1 caches to respond appropriately upon receiving a conditional request, including both a last modified date, e.g., in an if modified since or if unmodified since header field, and one or more entity tags, e.g., in an if match, if none match, or if range header field. An HTTP/1.1 origin server must not return a response status of 304, not modified, unless it is consistent with all conditional header fields. An HTTP/1.1 caching proxy should not return a locally cached response to the client. if that response is inconsistent with all conditional header fields in the request. The general principle behind these rules is for HTTP/1.1 servers and clients to transmit as much non-redundant information as possible, making conservative assumptions about the validators received. Generally, last modified values support transparent and efficient caching, so HTTP/1.1 origin servers should provide them. Only in rare cases where using a last modified value could lead to serious problems for an HTTP/1 system should it not be provided. The principle behind entity tags is that only the service author knows the semantics of a resource well enough to select an appropriate cache validation mechanism, and any validator comparison function more complex than byte equality would introduce complications. Therefore, comparisons of other headers, except last modified for compatibility with HTTP/1, are never used for validating cache entries. For response cacheability, details about how entities should be handled based on the information provided by origin servers and clients have been outlined. Unless specifically constrained by a cache control directive, a caching system may always store a successful response as a cache entry, may return it without validation if it is fresh, and may return it after successful validation if there is neither a cache validator nor an explicit expiration time associated with a response. We do not expect it to be cached, but certain caches may violate this expectation. For example, when little or no network connectivity is available, a client can usually detect that such a response was taken from a cache by comparing the date header to the current time. Note, some HTTP/1 caches are known to violate this expectation without providing any warning. However, in some cases, it might be inappropriate for a cache to retain an entity or to return it in response to a subsequent request. This might be because absolute semantic transparency is deemed necessary by the service author, or because of security or privacy considerations. Certain cache control directives are therefore provided so that the server can indicate that certain resource entities or portions thereof are not to be cached regardless of other considerations. Note that section 14.8 normally prevents a shared cache from saving and returning a response to a previous request if that request included an authorization header, a response received with a status code of 200, 203, 206, 300, 301, or 410 may be stored by a cache and used in reply to a subsequent request, subject to the expiration mechanism, unless a cache control directive prohibits caching. However, a cache that does not support the range and content range headers must not cache 206 partial content responses. A response received with any other status code, e.g. status codes 302 and 307, must not be returned in a reply to a subsequent request unless there are cache control directives or another headers that explicitly allow it. For example, these include the following: an expires header, a maxage, smaxage, must revalidate, proxy revalidate, public or private cache control directive. The purpose of an HTTP cache is to store information received in response to requests for use in responding to future requests. In many cases, a cache simply returns the appropriate parts of a response to the requester. However, if the cache holds a cache entry based on a previous response, it might have to combine parts of a new response with what is held in the cache entry. For the purpose of defining the behavior of caches and non-caching proxies, we divide HTTP headers into two categories: end-to-end headers, which are transmitted to the ultimate recipient of a request or response. End-to-end headers in responses must be stored as part of a cache entry and must be transmitted in any response formed from a cache entry. Hop-by-hop headers, which are meaningful only for a single transport level connection and are not stored by caches or forwarded by proxies. The following HTTP/1.1 headers are hop-by-hop headers: connection, keep alive, proxy authenticate, proxy authorization, T trailers, transferring coding, upgrade. All other headers defined by HTTP/1.1 are end-to-end headers. Other hop-by-hop headers must be listed in a connection header to be introduced into HTTP/1.1 or later. Some features of the HTTP/1.1 protocol, such as digest authentication, depend on the value of certain end-to-end headers. A transparent proxy should not modify an end-to-end header unless the definition of that header requires or specifically allows that. A transparent proxy must not modify any of the following fields in a request or response, and it must not add any of these fields if not already present: content location, contentem d5 etag. Last modified a transparent proxy must not modify any of the following fields in a response: expires. When a cache makes a validating request to a server, and the server provides a 304 not modified response, or a 206 partial content response, the cache then constructs a response to send to the requesting client. If the status code is 304 not modified, the cache uses the entity body stored in the cache entry as the entity body of this outgoing response. If the status code is 206 partial content and the etag or last modified headers match exactly, the cache may combine the contents stored in the cache entry with the new contents received in the response and use the result as the entity body of this outgoing response. The end-to-end headers stored in the cache entry are used for the constructed response, except that any stored warning headers with warn code 1XX, see section 14.46, must be deleted from the cache entry and the forwarded response. Any stored warning headers with warn code 2XX must be retained in the cache entry and the forwarded response. Any end-to-end headers provided in the 300 and 4 or 206 response must replace the corresponding headers from the cache entry unless the cache decides to remove the cache entry. It must also replace the end-to-end headers stored with the cache entry with corresponding headers received in the incoming response, except for warning headers as described immediately above. If a header field name in the incoming response matches more than one header in the cache entry, all such old headers must be replaced. In other words, the set of end-to-end headers received in the incoming response overrides all corresponding end-to-end headers stored with the cache entry, except for stored warning headers with warn code 1XX, which are deleted even if not overridden. Note, this rule allows an origin server to use a 304 not modified or a 206 partial content response to update any header associated with a previous response for the same entity or subranges thereof. Although it might not always be meaningful or correct to do so, this rule does not allow an origin server to use a 304 not modified or a 206 partial content response to entirely delete a header that it had provided with a previous response. A response might transfer only a subrange of the bytes of an entity body, either because the request included one or more range specifications, or because a connection was broken prematurely after several such transfers. A cache might have received several ranges of the same entity body. If a cache has a stored non-empty set of subranges for an entity and an incoming response transfers another subrange, the cache may combine the new subrange with the existing set if both the following conditions are met. Both the incoming response and the cache entry have a cache validator. The two cache validators match using the strong comparison function. See section 13.33. If either requirement is not met, the cache must use only the most recent partial response based on the date values transmitted with every response, and using the incoming response if these values are equal or missing, and must discard the other partial information. Use of server-driven content negotiation. Section 12.1. As indicated by the presence of a very header field in a response, alters the conditions and procedure by which a cache can use the response for subsequent requests. See section 14.44 for use of the very header field by servers. A server should use the very header field to inform a cache of what request header fields were used to select among multiple representations of a cacheable response subject to server-driven negotiation. The set of header fields named by the very field value is known as the selecting request headers. When the cache receives a subsequent request whose request URI specifies one or more cache entries, including a very header field, the cache must not use such a cache entry to construct a response to the new request unless all of the selecting request headers present in the new request match the corresponding stored request headers in the original request. The selecting request headers from two requests are defined to match if and only if the selecting request headers in the first request can be transformed to the selecting request headers in the second request by adding or removing linear white space LWS. At places where this is allowed by the corresponding BNF and slash, or combining multiple message header fields with the same field name, following the rules about message headers in section 4.2, a vary header field value of always fails to match, and subsequent requests on that resource can only be properly interpreted by the origin server if the selecting request header fields for the cached entry do not match the selecting request header fields of the new request. Then the cache must not use a cached entry to satisfy the request unless it first relays the new request to the origin server in a conditional request, and the server responds with 304, not modified, including an entity tag or content location that indicates the entity to be used. If an entity tag was assigned to a cached representation, the forwarded request should be conditional and include the entity tags in an if none match header field from all its cache entries for the resource. This conveys to the server the set of entities currently held by the cache, so that if any one of these entities matches the requested entity, the server can use the etag header field in its 304, not modified, response to tell the cache which entry is appropriate. If the entity tag of the new response matches that of an existing entry, the new response should be used to update the header fields of the existing entry, and the result must be returned to the client if any of the existing cache entries contains only partial content for the associated entity. Its entity tag should not be included in the if none match header field unless the request is for a range that would be fully satisfied by that entry. If a cache receives a successful response whose content location field matches that of an existing cache entry for the same request URI, whose entity tag differs from that of the existing entry, and whose date is more recent than that of the existing entry, the existing entry should not be returned in response to future requests and should be deleted from the cache for reasons of security and privacy. It is necessary to make a distinction between shared and non-shared caches. A non-shared cache is one that is accessible only to a single user. Accessibility in this case should be enforced by appropriate security mechanisms. All other caches are considered to be shared. Other sections of this specification place certain constraints on the operation of shared caches in order to prevent loss of privacy or failure of access controls, errors, or incomplete response cache behavior are not detailed here. A cache that receives an incomplete response, for example, with fewer bytes of data than specified in a content length header, may store the response. However, the cache must treat this as a partial response. Partial responses may be combined as described in section 1354. The result might be a full response or might still be partial. A cache must not return a partial response to a client without explicitly marking it as such using the 206 partial content status code. A cache must not return a partial response using a status code of 200 OK if a cache receives a 5XX response while attempting to revalidate an entry. It may either forward this response to the requesting client or act as if the server failed to respond. In the latter case, it may return a previously received response unless the cached entry includes the must revalidate cache control directive C section 149, unless the origin server explicitly prohibits the caching of their responses. The application of GET and head methods to any resources should not have side effects that would lead to erroneous behavior if these responses are taken from a cache. They may still have side effects, but a cache is not required to consider such side effects in its caching decisions. Caches are always expected to observe an origin server's explicit restrictions on caching. We note one exception to this rule. Since some applications have traditionally used GETs and heads with query URLs, those containing in the rel path part to perform operations with significant side effects, caches must not treat responses to such URIs as fresh unless the server provides an explicit expiration time. This specifically means that responses from HTTP/10 servers for such URIs should not be taken from a cache C section 911. For related information, the effect of certain methods performed on a resource at the origin server might cause one or more existing cache entries to become non-transparently invalid. That is, although they might continue to be fresh, they do not accurately reflect what the origin server would return for a new request on that resource. There is no way for the HTTP protocol to guarantee that all such cache entries are marked invalid. For example, the request that caused the change at the origin server might not have gone through the proxy where a cache entry is stored. However, several rules help reduce the likelihood of erroneous behavior in this section. The phrase invalidate an entity means that the cache will either remove all instances of that entity from its storage, or will mark these as invalid and in need of a mandatory revalidation before they can be returned in response to a subsequent request. Some HTTP methods must cause a cache to invalidate an entity. This is either the entity referred to by the request URI or by the location or content location headers. If present, these methods are put delete post in order to prevent denial of service attacks. An invalidation based on the URI in a location or content location header must only be performed if the host part is the same as in the request URI, a cache that passes through requests for methods it does not understand. SHOULD, invalidate any entities referred to by the request URI, all methods that might be expected to cause modifications to the origin server's resources must be written through to the origin server. This currently includes all methods except for GET, and head a cache must not reply to such a request from a client before having transmitted the request to the inbound server, and having received a corresponding response from the inbound server. This does not prevent a proxy cache from sending a 100 continue response before the inbound server has sent its final reply. The alternative known as write back or copy back caching is not allowed in HTTP/11 due to the difficulty of providing consistent updates and the problems arising from server cache or network failure prior to write back cache replacement. If a new cacheable response is received from a resource, while any existing responses for the same resource are cached, the cache should use the new response to reply to the current request. It may insert it into cache storage and may, if it meets all other requirements, use it to respond to any future requests that would previously have caused the old response to be returned. If it inserts the new response into cache storage, the rules in section 13.53 apply. Note, a new response that has an older date header value than existing cached responses is not cacheable. 13.13 History lists. User agents often have history mechanisms, such as back buttons and history lists, which can be used to redisplay an entity retrieved earlier in a session. History mechanisms and caches are different. In particular, history mechanisms should not try to show a semantically transparent view of the current state of a resource. Rather, a history mechanism is meant to show exactly what the user saw at the time when the resource was retrieved. By default, an expiration time does not apply to history mechanisms. If the entity is still in storage, a history mechanism should display it, even if the entity has expired, unless the user has specifically configured the agent to refresh expired history documents. This is not to be construed to prohibit the history mechanism from telling the user that a view might be stale. Note, if history list mechanisms unnecessarily prevent users from viewing stale resources, this will tend to force service authors to avoid using HTTP expiration controls and cache controls when they would otherwise like to. Service authors may consider it important that users not be presented with error messages or warning messages when they use navigation controls, such as back, to view previously fetched resources, even though sometimes such resources ought not to cache or ought to expire quickly. User interface considerations may force service authors to resort to other means of preventing caching, e.g., once-only URLs, in order not to suffer the effects of improperly functioning history mechanisms. 14 header field definitions. This section defines the syntax and semantics of all standard HTTP/1.1 header fields. For entity header fields, both sender and recipient refer to either the client or the server, depending on who sends and who receives the entity. 14.1 Accept. The accept request header field can be used to specify certain media types which are acceptable for the response. Accept headers can be used to indicate that the request is specifically limited to a small set of desired types, as in the case of a request for an inline image, accept equals accept /type/type/subtype, parameter media range equals /type/type/subtype, parameter accept params equals q equals q value accept extension equals token equals token quoted string. The asterisk character is used to group media types into ranges, with slash indicating all media types and type slash indicating all subtypes of that type. The media range may include media type parameters that are applicable to that range. Each media range may be followed by one or more accept params, beginning with the Q parameter for indicating a relative quality factor. The first Q parameter any separates the media range parameters from the accept params. Quality factors allow the user or user agent to indicate the relative degree of preference for that media range. Using the Q-value scale from 0 to 1, section 3.9, the default value is Q equals 1. Use of the Q parameter name to separate media type parameters from accept extension parameters is due to historical practice. Although this prevents any media type parameter named Q from being used with a media range, such an event is believed to be unlikely given the lack of any Q parameters in the IANA media type registry, and the rare usage of any media type parameters in accept. Future media types are discouraged from registering any parameter named Q. The example accept audio / Q equals 0.2, audio / basic SHOULD be interpreted as I prefer audio / basic, but send me any audio type if it is the best available after an 80% markdown in quality. If no accept header field is present, then it is assumed that the client accepts all media types. If an accept header field is present, and if the server cannot send a response which is acceptable according to the combined accept field value, then the server should send a 406 not acceptable response. A more elaborate example is accept text / plain Q equals 0.5 text / HTML text / XDVI Q equals 0.8 text / XC verbally. This would be interpreted as text / HTML and text / XC are the preferred media types. But if they do not exist, then send the text / XDVI entity. And if that does not exist, send the text / plain entity. Media ranges can be overridden by more specific media ranges or specific media types. If more than one media range applies to a given type, the most specific reference has precedence. For example, accept text / HTML text / HTML level equals 1 / have the following precedence: 1 text / HTML level equals 1 2 text / HTML3 text / 4 / the media type quality factor associated with a given type is determined by finding the media range with the highest precedence which matches that type. For example, accept text / Q equals 0.3 text / HTMLQ equals 0.7. Text slash HTML level equals 1. Text slash HTML level equals 2Q equals 0.4 slash Q equals 0.5 would cause the following values to be associated. Text slash HTML level equals 1 text slash HTML equals 0.7 text slash plain equals 0.3 image slash JPEG equals 0.5 text slash HTML level equals 2 equals 0.4 text slash HTML level equals 3 equals 0.7. Note: a user agent might be provided with a default set of quality values for certain media ranges. However, unless the user agent is a closed system which cannot interact with other rendering agents, this default set ought to be configurable by the user. 14.2 Accept charset. The accept charset request header field can be used to indicate what character sets are acceptable for the response. This field allows clients capable of understanding more comprehensive or special purpose character sets to signal that capability to a server which is capable of representing documents in those character sets. Accept charset equals accept charset. One number charset. Q equals Q value. Character set values are described in section 3.4. Each charset may be given an associated quality value which represents the user's preference for that charset. The default value is Q equals 1. An example is accept charset ISO 8859-5. Unicode -1-1Q equals 0.8. The special value, if present in the accept charset field, matches every character set, including is ominous 8859-1, which is not mentioned elsewhere in the accept charset field. If no is present in an accept charset field, then all character sets not explicitly mentioned get a quality value of 0, except for is ominous 8859-1, which gets a quality value of 1 if not explicitly mentioned. If no accept charset header is present, the default is that any character set is acceptable. If an accept charset header is present, and if the server cannot send a response which is acceptable according to the accept charset header, then the server should send an error response with the 406 not acceptable status code. Though the sending of an unacceptable response is also allowed. 14.3 Accepting coding. The accepting coding request header field is similar to accept, but restricts the content codings. Section 3.5 that are acceptable in the response. Accepting coding equals accepting coding. Token, pause 2's accepting coding field is used to indicate the content codings that the user agent can accept. Examples include compress gzip, compress q equals 0.5, gzip q equals 1, and gzip q equals 1, identity q equals 0.5, q equals 0. A server tests whether a content coding is acceptable based on an accepting coding field according to these rules. First, if the content coding is listed in the accepting coding field, it is acceptable unless accompanied by a Q value of 0. Second, the special symbol matches any available content coding not explicitly listed. Third, among multiple acceptable content codings, the one with the highest non-zero Q value is preferred. Fourth, identity content coding is always acceptable unless refused, because the accepting coding field includes identity Q equals 0 or Q equals 0 and does not include identity if the accepting coding field value is empty, then only identity encoding is acceptable. If a server cannot send a response that is acceptable according to the accepting coding header, it should send an error response with 406 not acceptable status code if no accepting coding field is present in a request. The server may assume any content coding is acceptable. If identity is available, use it unless additional information suggests otherwise. Note, without an accepting coding field, and if identity is unavailable, HTTP/1 common content codings like gzip and compress are preferred. Some older clients improperly display messages with other content codings. Note, most HTTP/1 applications do not recognize or obey Q values associated with content codings. The accept language request header field restricts the set of natural languages that are preferred as a response to the request. It is similar to accept, but focuses on language tags defined in section 3.1. Accept language. Accept language. 1 number language range. Q equals Q value. Each language range may be given an associated quality value which represents user preference for the languages specified by that range, defaulting to Q equals 1. For example, accept language de NGB Q equals 0.8, NQ equals 0.7 would mean I prefer Danish, but will accept British English and other types of English. A language range matches a language tag if it exactly equals the tag, or if it is a prefix of the tag such that the first tag character following the prefix is the special range, if present in the accept language field, matches every tag not matched by any other range. Note, the use of a prefix matching rule does not imply that languages are assigned to tags in such a way that understanding one tag means understanding all language tags for which it is a prefix. The language quality factor assigned to a language tag by the accept language field is the quality value of the longest language range in the field that matches the language tag. If no language range in the field matches the tag, the language quality factor assigned is 0. If no accept language header is present in the request, the server SHOULD assume that all languages are equally acceptable. If an accept language header is present, then all languages which are assigned a quality factor greater than 0 are acceptable. It might be contrary to the privacy expectations of the user to send an accept language header with the complete linguistic preferences of the user in every request. For a discussion of this issue, see section 15.14. As intelligibility is highly dependent on the individual user, it is recommended that client applications make the choice of linguistic preference available to the user. If the choice is not made available, then the accept language header field must not be given in the request. Note, when making the choice of linguistic preference available to the user, we remind implementors of the fact that users are not familiar with the details of language matching as described above, and should provide appropriate guidance. As an example, users might assume that on selecting NGB, they will be served any kind of English document if British English is not available. A user agent might suggest in such a case to add N to get the best matching behavior. 14.5. Accept ranges. The accept ranges response header field allows the server to indicate its acceptance of range requests for a resource. Accept ranges equals accept ranges. Acceptable ranges equals one number range unit. None origin servers that accept byte range requests may send accept ranges bytes, but are not required to do so. Clients may generate byte range requests without having received this header for the resource involved. Range units are defined in section 3.12. Servers that do not accept any kind of range request for a resource may send accept ranges. None to advise the client not to attempt a range request. 14.6 Age. The age response header field conveys the sender's estimate of the amount of time since the response, or its revalidation, was generated at the origin server. A cached response is fresh if its age does not exceed its freshness lifetime. Age values are calculated as specified in section 13.23. Age equals age. Age value equals delta seconds. Age values are non-negative decimal integers representing time in seconds. If a cache receives a value larger than the largest positive integer it can represent, or if any of its age calculations overflow, it must transmit an age header with a value of 2,147,483,648. 231. An HTTP/1.1 server that includes a cache must include an age header field in every response generated from its own cache. Caches should use an arithmetic type of at least 31 bits of range. 14.7 Allow. The allow entity header field lists the set of methods supported by the resource identified by the request URI. The purpose of this field is strictly to inform the recipient of valid methods associated with the resource. An allow header field must be present in a 405 method not allowed response. Allow equals allow. Number method example of use. Allow. Get. Head. Put this field cannot prevent a client from trying other methods. However, the indications given by the allow header field value should be followed. The actual set of allowed methods is defined by the origin server at the time of each request. The allow header field may be provided with a PUT request to recommend the methods to be supported by the new or modified resource. The server is not required to support these methods, and SHOULD include an allow header in the response giving the actual supported methods. A proxy must not modify the allow header field even if it does not understand all the methods specified, since the user agent might have other means of communicating with the origin server. 14.8 Authorization. A user agent that wishes to authenticate itself with a server usually, but not necessarily, after receiving a 401 response does so by including an authorization request header field with the request. The authorization field value consists of credentials containing the authentication information of the user agent for the realm of the resource being requested. Authorization equals authorization credentials. HTTP access authentication is described in HTTP authentication, basic and digest access authentication. 43. If a request is authenticated and a realm specified, the same credentials should be valid for all other requests within this realm, assuming that the authentication scheme itself does not require otherwise, such as credentials that vary according to a challenge value, or using synchronized clocks. When a shared cache receives a request containing an authorization field, it must not return the corresponding response as a reply to any other request unless one of the following specific exceptions holds. 1. If the response includes the sMessage cache control directive, the cache may use that response in replying to a subsequent request. But if the specified maximum age has passed, a proxy cache must first revalidate it with the origin server, using the request headers from the new request to allow the origin server to authenticate the new request. This is the defined behavior for sMessage. If the response includes sMessage equals 0, the proxy must always revalidate it before reusing it. 2. If the response includes the must revalidate cache control directive, the cache may use that response in replying to a subsequent request. But if the response is stale, all caches must first revalidate it with the origin server, using the request headers from the new request to allow the origin server to authenticate the new request. 3. If the response includes the public cache control directive, it may be returned in reply to any subsequent request. 14.9 Cache control. The cache control general header field is used to specify directives that must be obeyed by all caching mechanisms along the request/response chain. The directives specify behavior intended to prevent caches from adversely interfering with the request or response. These directives typically override the default caching algorithms. Cache directives are unidirectional in that the presence of a directive in a request does not imply that the same directive is to be given in the response. Note that HTTP/1 caches might not implement cache control and might only implement pragma, no cache. See section 14.32. Cache directives must be passed through by a proxy or gateway application, regardless of their significance to that application, since the directives might be applicable to all recipients along the request/response chain. It is not possible to specify a cache directive for a specific cache. Cache control equals cache control. One number cache directive equals cache request directive, cache response directive, cache request directive equals no cache. Section 14.91, no store. Section 14.92, max age equals delta seconds. Section 14.93, 14.94, max stale equals delta seconds. Section 14.93, min fresh equals delta seconds. Section 14.93, no transform. Section 14.95, only if cached. Section 14.94, cache extension. Section 14.96, cache response directive can have the value public. Section 14.91, or private, followed by equals, and then one to many field names in quotes. Section 14.91, or no cache, followed by equals, and then one to many field names in quotes. Section 14.91, or no store. Section 14.92, or no transform. Section 14.95, or must revalidate. Section 14.94, or proxy revalidate. Section 14.94, or max age, followed by equals, and then delta seconds. Section 14.93, or smaxage, followed by equals, and then delta seconds. Section 14.93, or cache extension, which is a token with an optional equals, followed by either a token or quoted string. Section 14.96. When a directive appears without any field name parameter, the directive applies to the entire request or response. When such a directive appears with a field name parameter, it applies only to the named field or fields, and not to the rest of the request or response. This mechanism supports extensibility. Implementations of future versions of the HTTP protocol might apply these directives to header fields not defined in HTTP/1.1. The cache control directives can be broken down into these general categories: restrictions on what are cacheable, which may only be imposed by the origin server; restrictions on what may be stored by a cache, which may be imposed by either the origin server or the user agent; modifications of the basic expiration mechanism, which may be imposed by either the origin server or the user agent; controls over cache revalidation and reload, which may only be imposed by a user agent; control over transformation of entities' extensions to the caching system. 14.91. What is cacheable by default? A response is cacheable if the requirements of the request method, request header fields, and the response status indicate that it is cacheable. Section 13.4 summarizes these defaults for cacheability. The following cache control response directives allow an origin server to override the default cacheability of a response. Public indicates that the response may be cached by any cache, even if it would normally be non-cacheable or cacheable only within a non-shared cache. Private indicates that all or part of the response message is intended for a single user and must not be cached by a shared cache. This allows an origin server to state that the specified parts of the response are intended for only one user and are not a valid response for requests by other users. A private, non-shared cache may cache the response. Note, this usage of the word private only controls where the response may be cached and cannot ensure the privacy of the message content. No cache. If the no cache directive does not specify a field name, then a cache must not use the response to satisfy a subsequent request without successful revalidation with the origin server. This allows an origin server to prevent caching even by caches that have been configured to return stale responses to client requests if the no cache directive does specify one or more field names. Then a cache may use the response to satisfy a subsequent request subject to any other restrictions on caching. However, the specified field names must not be sent in the response to a subsequent request without successful revalidation with the origin server. This allows an origin server to prevent the reuse of certain header fields in a response, while still allowing caching of the rest of the response. Note, most HTTP/1 caches will not recognize or obey this directive. The purpose of the no store directive is to prevent the inadvertent release or retention of sensitive information, for example, on backup tapes. The no store directive applies to the entire message and may be sent either in a response or in a request. If sent in a request, a cache must not store any part of either this request or any response to it. If sent in a response, a cache must not store any part of either this response or the request that elicited it. This directive applies to both non-shared and shared caches. Must not store in this context means that the cache must not intentionally store the information in non-volatile storage and must make a best effort attempt to remove the information from volatile storage as promptly as possible after forwarding it, even when this directive is associated with a response. Users might explicitly store such a response outside of the caching system, e.g., with a save as dialog. History buffers may store such responses as part of their normal operation. The purpose of this directive is to meet the stated requirements of certain users and service authors who are concerned about accidental releases of information via unanticipated accesses to cache data structures. While the use of this directive might improve privacy in some cases, we caution that it is not in any way a reliable or sufficient mechanism for ensuring privacy. In particular, malicious or compromised caches might not recognize or obey this directive, and communications networks might be vulnerable to eavesdropping. 14.93 Modifications of the basic expiration mechanism. The expiration time of an entity may be specified by the origin server using the expires header. See section 14.21. Alternatively, it may be specified using the maxage directive in a response. When the maxage cache control directive is present in a cached response, the response is stale if its current age is greater than the age value given in seconds. At the time of a new request for that resource, the maxage directive on a response implies that the response is cacheable, i.e., public, unless some other, more restrictive cache directive is also present. If a response includes both an expires header and a MaxAge directive. The MaxAge directive overrides the expires header, even if the expires header is more restrictive. This rule allows an origin server to provide, for a given response, a longer expiration time to an HTTP/1.1 or later cache than to an HTTP/1 cache. This might be useful if certain HTTP/1 caches improperly calculate ages or expiration times, perhaps due to desynchronized clocks. Many HTTP/1 cache implementations will treat an expires value that is less than or equal to the response date value as being equivalent to the cache control response directive, no cache. If an HTTP/1.1 cache receives such a response, and the response does not include a cache control header field, it should consider the response to be non-cacheable in order to retain compatibility with HTTP/1 servers. Note, an origin server might wish to use a relatively new HTTP cache control feature, such as the private directive, on a network including older caches that do not understand that feature. The origin server will need to combine the new feature with an expires field whose value is less than or equal to the date value. This will prevent older caches from improperly caching the response. If a response includes an SMaxage directive, then for a shared cache, but not for a private cache, the maximum age specified by this directive overrides the maximum age specified by either the MaxAge directive or the expires header. The SMaxage directive also implies the semantics of the proxy revalidate directive. See section 14.94, i.e., that the shared cache must not use the entry after it becomes stale to respond to a subsequent request without first revalidating it with the origin server. The SMaxage directive is always ignored by a private cache. Most older caches not compliant with this specification do not implement any cache control directives. An origin server wishing to use a cache control directive that restricts but does not prevent caching by an HTTP/1.1 compliant cache may exploit the requirement that the MaxAge directive overrides the expires header, and the fact that pre-HTTP/1.1 compliant caches do not observe the MaxAge directive. Other directives allow a user agent to modify the basic expiration mechanism. These directives may be specified on a request. MaxAge indicates that the client is willing to accept a response whose age is no greater than the specified time in seconds, unless the max stale directive is also included. The client is not willing to accept a stale response. MinFresh indicates that the client is willing to accept a response whose freshness lifetime is no less than its current age plus the specified time in seconds. That is, the client wants a response that will still be fresh for at least the specified number of seconds. Max stale indicates that the client is willing to accept a response that has exceeded its expiration time if max stale is assigned a value. Then the client is willing to accept a response that has exceeded its expiration time by no more than the specified number of seconds. If no value is assigned to max stale, then the client is willing to accept a stale response of any age. If a cache returns a stale response, either because of a max stale directive on a request, or because the cache is configured to override the expiration time of a response, the cache must attach a warning header to the stale response. Using warning 110, response is stale. A cache may be configured to return stale responses without validation, but only if this does not conflict with any must level requirements concerning cache validation, e.g., a must revalidate cache control directive if both the new request and the cached entry include MaxAge directives. Then the lesser of the two values is used for determining the freshness of the cached entry for that request. Sometimes a user agent might want or need to insist that a cache revalidate its cache entry with the origin server, and not just with the next cache along the path to the origin server, or to reload its cache entry from the origin server. End-to-end revalidation might be necessary if either the cache or the origin server has overestimated the expiration time of the cached response. End-to-end reload may be necessary if the cache entry has become corrupted for some reason. End-to-end revalidation may be requested either when the client does not have its own local cached copy, in which case we call it unspecified end-to-end revalidation, or when the client does have a local cached copy, in which case we call it specific end-to-end revalidation. The client can specify these three kinds of action using cache control request directives. End-to-end reload the request includes a no cache cache control directive. Or, for compatibility with HTTP/1 clients, Pragma. No cache. Field names must not be included with the no cache directive in a request. The server must not use a cached copy when responding to such a request. Specific end-to-end revalidation. The request includes a max age equals 0 cache control directive, which forces each cache along the path to the origin server to revalidate its own entry, if any, with the next cache or server. The initial request includes a cache validating conditional with the client's current validator. Unspecified end-to-end revalidation. The request includes a max age equals 0 cache control directive, which forces each cache along the path to the origin server to revalidate its own entry, if any, with the next cache or server. The initial request does not include a cache validating conditional. The first cache along the path, if any, that holds a cache entry for this resource includes a cache validating conditional with its current validator. Max A. When an intermediate cache is forced by means of a max age equals 0 directive to revalidate its own cache entry, and the client has supplied its own validator in the request. The supplied validator might differ from the validator currently stored with the cache entry. In this case, the cache may use either validator in making its own request without affecting semantic transparency. However, the choice of validator might affect performance. The best approach is for the intermediate cache to use its own validator when making its request. If the server replies with 304, not modified, then the cache can return its now validated copy to the client with a 200 OK response. If the server replies with a new entity and cache validator, however, the intermediate cache can compare the returned validator with the one provided in the client's request using the strong comparison function. If the client's validator is equal to the origin server's, then the intermediate cache simply returns 304, not modified. Otherwise, it returns the new entity with a 200 OK response. If a request includes the no cache directive, it should not include min fresh, max stale, or max A, only if cached. In some cases, such as times of extremely poor network connectivity, A client may want a cache to return only those responses that it currently has stored, and not to reload or revalidate with the origin server. To do this, the client may include the only if cached directive in a request. If it receives this directive, a cache should either respond using a cached entry that is consistent with the other constraints of the request, or respond with a 504 gateway timeout. Status, however, if a group of caches is being operated as a unified system with good internal connectivity, such a request may be forwarded within that group of caches. Must revalidate. Because a cache may be configured to ignore a server's specified expiration time, and because a client request may include a max stale directive, which has a similar effect. The protocol also includes a mechanism for the origin server to require revalidation of a cache entry on any subsequent use when the must revalidate directive is present in a response received by a cache. That cache must not use the entry after it becomes stale to respond to a subsequent request without first revalidating it with the origin server, i.e., the cache must do an end-to-end revalidation every time. If based solely on the origin server's expires or max age value, the cached response is stale. The must revalidate directive is necessary to support reliable operation for certain protocol features. In all circumstances, an HTTP/1.1 cache must obey the must revalidate directive. In particular, if the cache cannot reach the origin server for any reason, it must generate a 504 gateway timeout response. Servers should send the must revalidate directive if and only if failure to revalidate a request on the entity could result in incorrect operation, such as a silently unexecuted financial transaction. Recipients must not take any automated action that violates this directive, and must not automatically provide an unvalidated copy of the entity if revalidation fails. Although this is not recommended, user agents operating under severe connectivity constraints may violate this directive, but if so, must explicitly warn the user that an unvalidated response has been provided. The warning must be provided on each unvalidated access, and SHOULD require explicit user confirmation. Proxy revalidate. The proxy revalidate directive has the same meaning as the must revalidate directive, except that it does not apply to non-shared user-agent caches. It can be used on a response to an authenticated request to permit the user's cache to store and later return the response without needing to revalidate it, since it has already been authenticated once by that user, while still requiring proxies that service many users to revalidate each time in order to make sure that each user has been authenticated. Note that such authenticated responses also need the public cache control directive in order to allow them to be cached at all. 14.95 No Transform Directive. No transform. Implementors of intermediate caches. Proxies have found it useful to convert the media type of certain entity bodies. A non-transparent proxy might, for example, convert between image formats in order to save cache space or to reduce the amount of traffic on a slow link. Serious operational problems occur, however, when these transformations are applied to entity bodies intended for certain kinds of applications. For example, applications for medical imaging, scientific data analysis, and those using end-to-end authentication all depend on receiving an entity body that is bit for bit identical to the original entity body. Therefore, if a message includes the no transform directive, an intermediate cache or proxy must not change those headers that are listed in section 13.52 as being subject to the no transform directive. This implies that the cache or proxy must not change any aspect of the entity body that is specified by these headers, including the value of the entity body itself. 14.96 Cache control extensions. The cache control header field can be extended through the use of one or more cache extension tokens, each with an optional assigned value. Informational extensions, those which do not require a change in cache behavior, may be added without changing the semantics of other directives. Behavioral extensions are designed to work by acting as modifiers to the existing base of cache directives. Both the new directive and the standard directive are supplied such that applications which do not understand the new directive will default to the behavior specified by the standard directive, and those that understand the new directive will recognize it as modifying the requirements associated with the standard directive. In this way, extensions to the cache control directives can be made without requiring changes to the base protocol. This extension mechanism depends on an HTTP cache obeying all of the cache control directives defined for its native HTTP version, obeying certain extensions, and ignoring all directives that it does not understand. For example, consider a hypothetical new response directive called community, which acts as a modifier to the private directive. We define this new directive to mean that in addition to any non-shared cache, any cache which is shared only by members of the community named within its value may cache the response. An origin server wishing to allow the UCI community to use an otherwise private response in their shared caches could do so by including cache control. Private community equals UCI. A cache seeing this header field will act correctly even if the cache does not understand the community cache extension, since it will also see and understand the private directive, and thus default to the safe behavior. Unrecognized cache directives must be ignored. It is assumed that any cache directive likely to be unrecognized by an HTTP/1.1 cache will be combined with standard directives or the response's default cacheability, such that the cache behavior will remain minimally correct even if the cache does not understand the extensions. The connection general header field allows the sender to specify options that are desired for that particular connection and must not be communicated by proxies over further connections. The connection header has the following grammar connection equals connection. 1 number, connection token equals token, HTTP/1.1 proxies must parse the connection header field before a message is forwarded. And for each connection token in this field, remove any header fields from the message with the same name as the connection token. Connection options are signaled by the presence of a connection token in the connection header field, not by any corresponding additional header fields, since the additional header field may not be sent if there are no parameters associated with that connection option. Message headers listed in the connection header must not include end-to-end headers, such as cache control. HTTP/1.1 defines the close connection option for the sender to signal that the connection will be closed after completion of the response. For example, connection. Close in either the request or the response header fields indicates that the connection should not be considered persistent. Section 8.1. After the current request / response is complete, HTTP/1.1 applications that do not support persistent connections must include the close connection option in every message. A system receiving an HTTP/1 or lower version message that includes a connection header must, for each connection token in this field, remove and ignore any header fields from the message with the same name as the connection token. This protects against mistaken forwarding of such header fields by pre-HTTP/1.1 proxies. See section 19.62. The content encoding entity header field is used as a modifier to the media type. When present, its value indicates what additional content codings have been applied to the entity body, and thus what decoding mechanisms must be applied in order to obtain the media type referenced by the content type header field. Content encoding is primarily used to allow a document to be compressed without losing the identity of its underlying media type. Content encoding equals content encoding. One number content codings are defined in section 3.5. An example of its use is content encoding. gzip, the content coding, is a characteristic of the entity identified by the request URI. Typically, the entity body is stored with this encoding and is only decoded before rendering or analogous usage. However, a non-transparent proxy may modify the content coding if the new coding is known to be acceptable to the recipient, unless the no transform cache control directive is present in the message. If the content coding of an entity is not identity, then the response must include a content encoding entity header. Section 14.11 that lists the non-identity content codings used if the content coding of an entity in a request message is not acceptable to the origin server. The server should respond with a status code of 415, unsupported media type, if multiple encodings have been applied to an entity. The content codings must be listed in the order in which they were applied. Additional information about the encoding parameters may be provided by other entity header fields not defined by this specification. The content language entity header field describes the natural languages of the intended audience for the enclosed entity. Note that this might not be equivalent to all the languages used within the entity body. Content language equals content language. One number language tags are defined in section 3.1. The primary purpose of content language is to allow a user to identify and differentiate entities according to the user's own preferred language. Thus, if the body content is intended only for a Danish literate audience, the appropriate field is content language. If no content language is specified, the default is that the content is intended for all language audiences. This might mean that the sender does not consider it to be specific to any natural language, or that the sender does not know for which language it is intended. Multiple languages may be listed for content that is intended for multiple audiences. For example, a rendition of the Treaty of Waitangi presented simultaneously in the original Maori and English versions would call for content language me, N. However, just because multiple languages are present within an entity does not mean that it is intended for multiple linguistic audiences. An example would be a beginner's language primer, such as a first lesson in Latin, which is clearly intended to be used by an English literate audience. In this case, the content language would properly only include N. Content language may be applied to any media type. It is not limited to textual documents. 14.13 Content length. The content length entity header field indicates the size of the entity body in decimal number of octettes sent to the recipient, or in the case of the head method, the size of the entity body that would have been sent had the request been a GET. Content length equals content length 1 digit. An example is content length 3495. Applications should use this field to indicate the transfer length of the message body, unless this is prohibited by the rules in section 4.4. Any content length greater than or equal to 0 is a valid value. Section 4.4 describes how to determine the length of a message body if a content length is not given. Note that the meaning of this field is significantly different from the corresponding definition in MIME, where it is an optional field used within the message/external body content type. In HTTP, it should be sent whenever the message's length can be determined prior to being transferred, unless this is prohibited by the rules in section 4.4. 14.14 Content Location. The content location entity header field may be used to supply the resource location for the entity enclosed in the message when that entity is accessible from a location separate from the requested resources URI. A server should provide a content location for the variant corresponding to the response entity, especially in the case where a resource has multiple entities associated with it, and those entities actually have separate locations by which they might be individually accessed. The server should provide a content location for the particular variant which is returned. Content location equals content location, absolute URI, relative URI. The value of content location also defines the base URI for the entity. The content location value is not a replacement for the original requested URI. It is only a statement of the location of the resource corresponding to this particular entity at the time of the request. Future requests may specify the content location URI as the request URI if the desire is to identify the source of that particular entity. A cache cannot assume that an entity with a content location different from the URI used to retrieve. It can be used to respond to later requests on that content location URI. However, the content location can be used to differentiate between multiple entities retrieved from a single requested resource, as described in section 13.6. If the content location is a relative URI, the relative URI is interpreted relative to the request URI. The meaning of the content location header in PUT or post requests is undefined. Servers are free to ignore it in those cases. 14.15 Contentem D5. The Contentem D5 entity header, field as defined in RFC 1864, is an MD5 digest of the entity body for the purpose of providing an end-to-end message integrity check, MIC, of the entity body contentem D5 equals contentem D5, MD5 digest. MD5 digest equals base 64 of 128 bit MD5 digest as per RFC 1864. The contentem D5 header field may be generated by an origin server or client to function as an integrity check of the entity body. Only origin servers or clients may generate the contentem D5 header field. Proxies and gateways must not generate it, as this would defeat its value as an end-to-end integrity check. Any recipient of the entity body, including gateways and proxies, may check that the digest value in this header field matches that of the entity body as received. The MD5 digest is computed based on the content of the entity body, including any content coding that has been applied, but not including any transferring coding applied to the message body. If the message is received with a transferring coding, that encoding must be removed prior to checking the contentem D5 value against the received entity. This has the result that the digest is computed on the octets of the entity body exactly as, and in the order that they would be sent if no transferring coding were being applied. HTTP extends RFC 1864 to permit the digest to be computed for MIME composite media types, e.g. multipart slash and message slash RFC 822. But this does not change how the digest is computed as defined in the preceding paragraph. There are several consequences of this. The entity body for composite types may contain many body parts, each with its own MIME and HTTP headers, including contentem D5, content transferring coding, and content encoding headers. If a body part has a content transferring coding or content encoding header, it is assumed that the content of the body part has had the encoding applied, and the body part is included in the contentem D5 digest, as is i.e. after the application, the transferring coding header field is not allowed within body parts. Conversion of all line breaks to CRLF must not be done before computing or checking the digest. The line break convention used in the text actually transmitted must be left unaltered when computing the digest. Note, while the definition of contentem D5 is exactly the same for HTTP as in RFC 1864 for MIME entity bodies. There are several ways in which the application of Content MD5 to HTTP entity bodies differs from its application to MIME entity bodies. One is that HTTP, unlike MIME, does not use content transfer encoding and does use transfer encoding and content encoding. Another is that HTTP more frequently uses binary content types than MIME. So it is worth noting that, in such cases, the byte order used to compute the digest is the transmission byte order defined for the type. Lastly, HTTP allows transmission of text types with any of several line break conventions, and not just the canonical form using CRLF 14.16 content range. The content range entity header is sent with a partial entity body to specify where in the full entity body the partial body should be applied. Range units are defined in section 3.12. Content range equals content range. Content range spec equals byte content range spec equals bytes unit SB byte range resp spec / instance length byte range resp spec equals first byte pose, last byte pose. Instance length equals 1 digit. The header should indicate the total length of the full entity body. Unless this length is unknown or difficult to determine, the asterisk character means that the instance length is unknown at the time when the response was generated. Unlike byte range's specifier values, see section 14.351. A byte range resp spec must only specify one range and must contain absolute byte positions for both the first and last byte of the range. A byte content range spec with a byte range resp spec whose last byte pose value is less than its first byte pose value, or whose instance length value is less than or equal to its last byte pose value, is invalid. The recipient of an invalid byte content range spec must ignore it, and any content transferred along with it. A server sending a response with status code 416, requested range not satisfiable, SHOULD, include a content range field with a byte range resp spec of the instance length specifies the current length of the selected resource. A response with status code 206 partial content must not include a content range field with a byte range resp spec. Examples of byte content range spec values, assuming that the entity contains a total of 1,234 bytes. The first 500 bytes, bytes 0-499/1234, the second 500 bytes. Bytes 500-999/1234, all except for the first 500 bytes, bytes 500-1234. The last 500 bytes, bytes 733/1234. When an HTTP message includes the content of a single range, for example, a response to a request for a single range, or to a request for a set of ranges that overlap without any holes. This content is transmitted with a content range header and a content length header showing the number of bytes actually transferred. For example, HTTP/1.1200 and 6 partial content date. WED 15/1995, 6:25 and 24 seconds. GMT last modified. WED 15/1995, 4:58 and 8 seconds. GMT content range. Bytes 21,000 and 10 minutes, 47,021 / 47,022 content length, 26,012 content type. Image/GIF. When an HTTP message includes the content of multiple ranges, for example, a response to a request for multiple non-overlapping ranges. These are transmitted as a multi-part message. The multi-part media type used for this purpose is multi-part/byte ranges, as defined in Appendix 19.2. See Appendix 19.63 for a compatibility issue. A response to a request for a single range must not be sent using the multi-part/byte ranges media type. A response to a request for multiple ranges, whose result is a single range, may be sent as a multi-part/byte ranges media type with one part. A client that cannot decode a multi-part/byte ranges message must not ask for multiple byte ranges in a single request. When a client requests multiple byte ranges in one request, the server should return them in the order that they appeared in the request. If the server ignores a byte range spec because it is syntactically invalid, the server should treat the request as if the invalid range header field did not exist. Normally, this means return a 200 response containing the full entity if the server receives a request other than one including an if range request header field with an unsatisfiable range request header field, that is, all of whose byte range spec values have a first byte pose value greater than the current length of the selected resource. It should return a response code of 416, requested range not satisfiable. Section 10.417. Note: clients cannot depend on servers to send a 416 requested range not satisfiable response instead of a 200 OK response for an unsatisfiable range request header. Since not all servers implement this request header, 14.17 content type. The content type entity header field indicates the media type of the entity body sent to the recipient, or in the case of the head method, the media type that would have been sent had the request been a GET. Content type equals content type. Media types are defined in section 3.7. An example of the field is content type. Text/HTML charset equals is ominous 8,859 minutes for further discussion of methods for identifying the media type of an entity is provided in section 7.21, 14.18 date. The date general header field represents the date and time at which the message was originated, having the same semantics as org date in RFC 822. The field value is an HTTP date, as described in section 3.31. It must be sent in RFC 1123 8-date format. Date equals date. HTTP date, an example, is date 2/15/1994 8:12 and 31 seconds GMT. Origin servers must include a date header field in all responses, except in these cases: 1. If the response status code is 100 continue, or 101 switching protocols, the response may include a date header field at the server's option. 2. If the response status code conveys a server error, e.g. 500 internal server error, or 503 service unavailable, and it is inconvenient or impossible to generate a valid date. 3. If the server does not have a clock that can provide a reasonable approximation of the current time, its responses must not include a date header field. In this case, the rules in section 14.181 must be followed. A received message without a date header field must be assigned 1 by the recipient if the message will be cached or gatewayed via a protocol requiring a date. An HTTP implementation without a clock must not cache responses without revalidating them on every use. An HTTP cache, especially a shared cache, SHOULD, use a mechanism such as NTP to synchronize its clock with a reliable external standard. Clients should only send a date header field in messages that include an entity body, like PUT and POST requests, but it is optional. A client without a clock must not send a date header field in a request. The HTTP date sent in a date header should not represent a date and time subsequent to the generation of the message. It should represent the best available approximation of the date and time of message generation, unless the implementation has no means of generating a reasonably accurate date and time. In theory, the date ought to represent the moment just before the entity is generated. In practice, the date can be generated at any time during the message origination without affecting its semantic value. 14.181 Clockless Origin Server Operation. Some origin server implementations might not have a clock available. An origin server without a clock must not assign expires or last modified values to a response unless these values were associated with the resource by a system or user with a reliable clock. It may assign an expires value that is known at or before server configuration time to be in the past. This allows pre-expiration of responses without storing separate expires values for each resource. 14.19 ETAG. The ETAG response header field provides the current value of the entity tag for the requested variant. The headers used with entity tags are described in sections 14.24, 14.26, and 14.44. The entity tag may be used for comparison with other entities from the same resource. See section 13.33. ETAG equals ETAG. Entity tag examples. ETAG XYZ etag, w/XYZ etag 14.2 expect. The expect request header field is used to indicate that particular server behaviors are required by the client. Expect equals expect. One number expectation equals 100 continue. Expectation extension equals token quoted string. Expect params equals token quoted string. A server that does not understand or is unable to comply with any of the expectation values in the expect field of a request must respond with appropriate error status. The server must respond with a 417 expectation failed status if any of the expectations cannot be met, or if there are other problems with the request, some other 4XX status. This header field is defined with extensible syntax to allow for future extensions. If a server receives a request containing an expect field that includes an expectation extension that it does not support, it must respond with a 417 expectation failed status. Comparison of expectation values is case insensitive for unquoted tokens, including the 100 continue token, and is case sensitive for quoted string expectation extensions. The expect mechanism is hop by hop, that is, an HTTP/1.1 proxy must return a 417 expectation failed status if it receives a request with an expectation that it cannot meet. However, the expect request header itself is end-to-end. It must be forwarded if the request is forwarded. Many older HTTP/1 and HTTP/1.1 applications do not understand the expect header. See section 8.23 for the use of the 100 continue status. The expires entity header field gives the date/time after which the response is considered stale. A stale cache entry may not normally be returned by a cache, either a proxy cache or a user agent cache, unless it is first validated with the origin server or with an intermediate cache that has a fresh copy of the entity. See section 13.2 for further discussion of the expiration model. The presence of an expires field does not imply that the original resource will change or cease to exist at, before, or after that time. The format is an absolute date and time as defined by HTTP date in section 3.31. It must be in RFC 1123 date format. Expires equals expires. HTTP date, an example of its use, is expires. 1 Dec 1994-16 and 0 seconds. GMT note: if a response includes a cache control field with the MaxAge directive, see section 14.93. That directive overrides the expires field. HTTP/1.1 clients and caches must treat other invalid date formats, especially including the value 0, as in the past, i.e., already expired, to mark a response as already expired. An origin server sends an expires date that is equal to the date header value. See the rules for expiration calculations in section 13.24. To mark a response as never expires, an origin server sends an expires date approximately 1 year from the time the response is sent. HTTP/1.1 servers should not send expires dates more than 1 year in the future. The presence of an expires header field with a date value of some time in the future on a response that otherwise would by default be non-cacheable indicates that the response is cacheable, unless indicated otherwise by a cache control header field. Section 14.9, 14.22 from request header field. If given, SHOULD contain an internet email address for the human user who controls the requesting user agent. The address should be machine usable as defined by mailbox in RFC 822. 9. As updated by RFC 1123.8 from equals from mailbox. An example is from webmaster@w3.org. This header field may be used for logging purposes and as a means for identifying the source of invalid or unwanted requests. It should not be used as an insecure form of access protection. The interpretation of this field is that the request is being performed on behalf of the person given, who accepts responsibility for the method performed. In particular, robot agents should include this header so that the person responsible for running the robot can be contacted if problems occur on the receiving end. The internet email address in this field may be separate from the internet host which issued the request. For example, when a request is passed through a proxy, the original issuer's address should be used. The client should not send the from header field without the user's approval, as it might conflict with the user's privacy interests or their site's security policy. It is strongly recommended that the user be able to disable, enable, and modify the value of this field at any time prior to a request. 14.23 Host. The host request header field specifies the internet host and port number of the resource being requested, as obtained from the original URI given by the user or referring resource, generally an HTTP URL, as described in section 3.22. The host field value must represent the naming authority of the origin server or gateway given by the original URL. This allows the origin server or gateway to differentiate between internally ambiguous URLs, such as the root/URL of a server for multiple host names on a single IP address. Host equals host. Host port section 3.22. A host without any trailing port information implies the default port for the service requested, e.g. 80 for an HTTP URL. For example, a request on the origin server for HTTP www.w3.org/pub/www/ would properly include get/pub/www/http/1.1 host www.w3.org. A client must include a host header field in all HTTP/1.1 request messages if the requested URI does not include an internet host name for the service being requested. Then the host header field must be given with an empty value. An HTTP/1.1 proxy must ensure that any request message it forwards does contain an appropriate host header field that identifies the service being requested by the proxy. All internet-based HTTP/1.1 servers must respond with a 400 bad request status code to any HTTP/1.1 request message which lacks a host header field. See sections 5.2 and 19.6.1.1 for other requirements relating to host. The if match request header field is used with a method to make it conditional. A client that has one or more entities previously obtained from the resource can verify that one of those entities is current by including a list of their associated entity tags in the if-match header field. Entity tags are defined in section 3.11. The purpose of this feature is to allow efficient updates of cached information with a minimum amount of transaction overhead. It is also used on updating requests to prevent inadvertent modification of the wrong version of a resource. As a special case, the value matches any current entity of the resource. If match equals if match : asterisk or one entity tag. If any of the entity tags match the entity tag of the entity that would have been returned in the response to a similar GET request without the if match header on that resource, or if asterisk is given and any current entity exists for that resource, then the server may perform the requested method as if the if match header field did not exist. A server must use the strong comparison function defined in section 13.33 to compare the entity tags in if match. If none of the entity tags match, or if asterisk is given and no current entity exists, the server must not perform the requested method and must return a 412 precondition failed response. This behavior is most useful when the client wants to prevent an updating method, such as PUT, from modifying a resource that has changed since the client last retrieved it. If the request would, without the if match header, result in anything other than a 2XX or 412 status, then the if match header must be ignored. The meaning of if match asterisk is that the method should be performed if the representation selected by the origin server or by a cache using the very mechanism exists, and must not be performed if the representation does not exist. A request intended to update a resource, such as a PUT, may include an if match header field to signal that the request method must not be applied if the entity corresponding to the if match value, a single entity tag, is no longer a representation of that resource. This allows the user to indicate that they do not wish the request to be successful if the resource has been changed without their knowledge. Examples: if match quotation mark Zizi quotation mark if match quotation mark Zizi, RD XXXX, C3 Piaz quotation mark if match asterisk. The result of a request having both an if match header field and either an if none match or an if modified since header field is undefined by this specification. 14.25. If modified since. The if modified since request header field is used with a method to make it conditional. If the requested variant has not been modified since the time specified in this field, an entity will not be returned from the server. Instead, a 304 not modified response will be returned without any message body. If modified since equals if modified since : HTTP date. An example of the field is if modified since sat, 29 oct 1994-1943 and 31 seconds GMT quotation. Mark a GET method with an if modified since header and no range header requests that the identified entity be transferred only if it has been modified since the date given by the if modified since header. The algorithm for determining this includes the following cases. A. If the request would normally result in anything other than a 200 OK status, or if the past if modified since date is invalid, the response is exactly the same as for a normal get. A date which is later than the server's current time is invalid. B. If the variant has been modified since the if modified since date, the response is exactly the same as for a normal get. C. If the variant has not been modified since a valid if modified since date, the server should return a 304 not modified response. The purpose of this feature is to allow efficient updates of cached information with a minimum amount of transaction overhead. Note, the range request header field modifies the meaning of if modified since. See section 14.35 for full details. Note, if modified since times are interpreted by the server, whose clock might not be synchronized with the client. Note, when handling an if modified since header field, some servers will use an exact date comparison function rather than a less than function for deciding whether to send a 304 not modified response to get best results when sending an if modified since header field for cache validation. Clients are advised to use the exact date string received in a previous last modified header field whenever possible. Note, if a client uses an arbitrary date in the if modified since header, instead of a date taken from the last modified header for the same request, the client should be aware that this date is interpreted in the server's understanding of time. The client should consider unsynchronized clocks and rounding problems due to different encodings of time between the client and server. This includes the possibility of race conditions if the document has changed between the time it was first requested and the if modified since date of a subsequent request, and the result of a request having both an if modified since header field and either an if match or an if unmodified since header fields is undefined by this specification. 14.26 If none match. The if none match request header field is used with a method to make it conditional. A client that has one or more entities previously obtained from the resource can verify that none of those entities is current by including a list of their associated entity tags in the if none match header field. The purpose of this feature is to allow efficient updates of cached information with a minimum amount of transaction overhead. It is also used to prevent a method, e.g., PUT, from inadvertently modifying an existing resource when the client believes that the resource does not exist. As a special case, the value matches any current entity of the resource. If none match equals if none match, one number entity tag. If any of the entity tags match the entity tag of the entity that would have been returned in the response to a similar GET request, without the if none match header on that resource, or if A is given and any current entity exists for that resource, then the server must not perform the requested method unless required to do so, because the resource's modification date fails to match that supplied in an if modified since header field in the request. Instead, if the request method was GET or HEAD, the server should respond with a 304 not modified response, including the cache-related header fields, particularly eTag, of one of the entities that matched for all other request methods. The server must respond with a status of 412, precondition failed. See section 13.33 for rules on how to determine if two entity tags match. The weak comparison function can only be used with GAT or head requests. If none of the entity tags match, then the server may perform the requested method, as if the if none match header field did not exist, but must also ignore any if modified since header fields in the request. That is, if no entity tags match, then the server must not return a 304 not modified response. If the request would, without the if none match header field, result in anything other than a 2XX or 304 status, then the if none match header must be ignored. See section 13.34 for a discussion of server behavior when both if modified since and if none match appear in the same request. The meaning of if none match is that the method must not be performed if the representation selected by the origin server or by a cache, possibly using the very mechanism. See section 14.44 exists and should be performed if the representation does not exist. This feature is intended to be useful in preventing races between PUT operations. Examples: if none match, XYZ if none match, w/XYZ if none match, XYZ RDXXXX, C3PRs if none match, w/XYZ, w/RDXXXX, w/C3PRs if none match, the result of a request having both an if none match header field and either an if match or an if unmodified since header fields is undefined by this specification. 14.27 if rain. If a client has a partial copy of an entity in its cache and wishes to have an up-to-date copy of the entire entity in its cache, it could use the range request header with a conditional get, using either or both of if unmodified since and if match. However, if the condition fails because the entity has been modified, the client would then have to make a second request to obtain the entire current entity body. The if range header allows a client to short-circuit the second request. Informally, its meaning is, if the entity is unchanged, send me the parts that I am missing. Otherwise, send me the entire new entity. If range equals if range. Entity tag HTTP date. If the client has no entity tag for an entity, but does have a last modified date, it may use that date in an if range header. The server can distinguish between a valid HTTP date and any form of entity tag by examining no more than 2 characters. The if range header should only be used together with a range header and must be ignored if the request does not include a range header. or if the server does not support the subrange operation, if the entity tag given in the if range header matches the current entity tag for the entity, then the server should provide the specified subrange of the entity using a 206 partial content response. If the entity tag does not match, then the server should return the entire entity using a 200 OK response. 14.28 If unmodified since. The if unmodified since request header field is used with a method to make it conditional if the requested resource has not been modified since the time specified in this field. The server should perform the requested operation as if the if unmodified since header were not present. If the requested variant has been modified since the specified time, the server must not perform the requested operation and must return a 412 precondition failed if unmodified since equals if unmodified since. HTTP date, an example of the field, is if unmodified since SAT 29 Oct 1994-1943 and 31 seconds GMT. If the request, normally i.e. without the if unmodified since header, would result in anything other than a 2XX or 412 status, the if unmodified since header should be ignored. If the specified date is invalid, the header is ignored. The result of a request having both an if unmodified since header field and either an if none match or an if modified since header fields is undefined by this specification. 14.29 Last modified. The last modified entity header field indicates the date and time at which the origin server believes the variant was last modified. Last modified equals last modified. HTTP date, an example of its use, is last modified. 2. 15 Nov 1994, 12:45 and 26 seconds GMT. The exact meaning of this header field depends on the implementation of the origin server and the nature of the original resource. For files, it may be just the file system last modified time. For entities with dynamically included parts, it may be the most recent of the set of last modified times for its component parts. For database gateways, it may be the last update timestamp of the record. For virtual objects, it may be the last time the internal state changed. An origin server must not send a last modified date, which is later than the server's time of message origination. In such cases, or the resource's last modification would indicate some time in the future. The server must replace that date with the message origination date. An origin server, SHOULD, obtain the last modified value of the entity as close as possible to the time that it generates the date value of its response. This allows a recipient to make an accurate assessment of the entity's modification time, especially if the entity changes near the time that the response is generated. HTTP/1.1 servers should send last modified whenever feasible. Location response header field is used to redirect the recipient to a location other than the request URI for completion of the request or identification of a new resource for 201 created responses. The location is that of the new resource which was created by the request for 3XX responses. The location should indicate the server's preferred URI for automatic redirection to the resource. The field value consists of a single absolute URI. Location equals location. Absolute URI, an example, is location. HTTP www.w3.org/www/peoplehtml. Note, the content location header field differs from location in that the content location identifies the original location of the entity enclosed in the request. It is therefore possible for a response to contain header fields for both location and content location. Also see section 13.1 for cache requirements of some methods. Max Forward's request header field provides a mechanism with the trace and options methods to limit the number of proxies or gateways that can forward the request to the next inbound server. This can be useful when the client is attempting to trace a request chain which appears to be failing or looping in mid-chain. Max forwards equals max forwards. One digit, the max forwards value, is a decimal integer indicating the remaining number of times this request message may be forwarded each proxy or gateway recipient of a trace or options request containing a max forwards header field must check and update its value prior to forwarding the request if the received value is 0. The recipient must not forward the request. Instead, it must respond as the final recipient if the received max forwards value is greater than 0. Then, the forwarded message must contain an updated max forwards field with a value decremented by 1-1. The max forwards header field may be ignored for all other methods defined by this specification, and for any extension methods for which it is not explicitly referred to as part of that method definition. Pragma general header field is used to include implementation specific directives that might apply to any recipient along the request/response chain. All Pragma directives specify optional behavior from the viewpoint of the protocol. However, some systems may require that behavior be consistent with the directives. Pragma equals Pragma, one number Pragma directive equals no cache extension Pragma equals token quoted string. When the no cache directive is present in a request message, an application SHOULD forward the request toward the origin server, even if it has a cached copy of what is being requested. This Pragma directive has the same semantics as the no cache directive and is defined here for backward compatibility with HTTP/1. Clients should include both header fields when a no cache request is sent to a server not known to be HTTP/1.1 compliant. Pragma directives must be passed through by a proxy or gateway application, regardless of their significance to that application, since the directives might be applicable to all recipients along the request/response chain. It is not possible to specify a Pragma for a specific recipient. However, any Pragma directive not relevant to a recipient should be ignored by that recipient. HTTP/1.1 caches should treat Pragma no cache as if the client had sent cache control. No cache. No new Pragma directives will be defined in HTTP. Note, because the meaning of Pragma, no cache as a response header field, is not actually specified, it does not provide a reliable replacement for cache control. No cache in a response. Proxy authenticate response header field must be included as part of a 407 proxy authentication. Required response. The field value consists of a challenge that indicates the authentication scheme and parameters applicable to the proxy for this request URI. The HTTP access authentication process is described in HTTP authentication, basic and digest access authentication 43. Unlike www authenticate, the proxy authenticate header field applies only to the current connection and should not be passed on to downstream clients. However, an intermediate proxy might need to obtain its own credentials by requesting them from the downstream client, which in some circumstances will appear as if the proxy is forwarding the proxy authenticate header field. 14.34 Proxy authorization. The proxy authorization request header field allows the client to identify itself or its user to a proxy which requires authentication. The proxy authorization field value consists of credentials containing the authentication information of the user, agent for the proxy, and slash or realm of the resource being requested. Proxy authorization equals proxy authorization. Credentials. The HTTP access authentication process is described in HTTP authentication. Basic and digest access authentication. 43. Unlike authorization, the proxy authorization header field applies only to the next outbound proxy that demanded authentication using the proxy authenticate field. When multiple proxies are used in a chain, the proxy authorization header field is consumed by the first outbound proxy that was expecting to receive credentials. A proxy may relay the credentials from the client request to the next proxy if that is the mechanism by which the proxies cooperatively authenticate a given request. 14.35 range. 14.3 51 byte ranges. Since all HTTP entities are represented in HTTP messages as sequences of bytes, the concept of a byte range is meaningful for any HTTP entity. However, not all clients and servers need to support byte range operations. Byte range specifications in HTTP apply to the sequence of bytes in the entity body, not necessarily the same as the message body. Ranges specifier equals byte ranges specifier equals bytes unit equals byte range set equals one number. Byte range spec suffix byte range spec. Byte range spec equals first byte pose. Last byte pos first byte pose equals 1 digit last byte pose equals 1 digit. The first byte pose value in a byte range spec gives the byte offset of the first byte in a range. The last byte pose value gives the byte offset of the last byte in the range. That is, the byte positions specified are inclusive. Byte offsets start at 0 If the last byte pose value is present, it must be greater than or equal to the first byte pose in that byte range spec, or the byte range spec is syntactically invalid, the recipient of a byte range set that includes one or more syntactically invalid byte range spec values must ignore the header field that includes that byte range set if the last byte pose value is absent, or if the value is greater than or equal to the current length of the entity body. Last byte pose is taken to be equal to one less than the current length of the entity body in bytes by its choice of last byte pose. A client can limit the number of bytes retrieved without knowing the size of the entity. Suffix byte range spec equals suffix length equals 1 digit. A suffix byte range spec is used to specify the suffix of the entity body of a length given by the suffix length value. That is, this form specifies the last n bytes of an entity body. If the entity is shorter than the specified suffix length, the entire entity body is used. If a syntactically valid byte range set includes at least one byte range spec whose first byte pose is less than the current length of the entity body, or at least one suffix byte range spec with a non-zero suffix length, then the byte range set is satisfiable. Otherwise, the byte range set is unsatisfiable. If the byte range set is unsatisfiable, the server should return a response with a status of 416. Requested range not satisfiable. Otherwise, the server should return a response with a status of 206 partial content containing the satisfiable ranges of the entity body. Examples of byte ranges specifier values, assuming an entity body of length 10,000, are as follows. The first 500 bytes, byte offsets 0-499, inclusive bytes equals 0-499. The second 500 bytes, byte offsets 500-999, inclusive bytes equals 500-999. The final 500 bytes, byte offsets 95, 0-9,999, inclusive bytes equals -500 or bytes equals 95, 0. The first and last bytes, only bytes 0 and 9999. Bytes equals 00, -1 several legal but not canonical specifications of the second 500 bytes. Byte offsets 500 minus 999. Inclusive, bytes equals 500 minus 600,000. 600. And 1 minus 999 bytes equals 500 minus 700,000. 600. And 1 minus 999 range retrieval requests, HTTP retrieval requests, using conditional or unconditional GET methods, may request one or more subranges of the entity instead of the entire entity, using the range request header, which applies to the entity returned as the result of the request. Range equals range. Range's specifier, a server, may ignore the range header. However, HTTP/1.1 origin servers and intermediate caches ought to support byte ranges when possible, since range supports efficient recovery from partially failed transfers and supports efficient partial retrieval of large entities if the server supports the range header and the specified range or ranges are appropriate for the entity. The presence of a range header in an unconditional GET modifies what is returned if the GET is otherwise successful. In other words, the response carries a status code of 206 partial content instead of 200 OK. The presence of a range header in a conditional get a request using one or both of if modified since and if none match, or one or both of if unmodified since and if match modifies what is returned if the GET is otherwise successful and the condition is true. It does not affect the 304 not modified response returned if the conditional is false. In some cases, it might be more appropriate to use the if range header C section 14.27 in addition to the range header if a proxy that supports ranges receives a range request, forwards the request to an inbound server, and receives an entire entity in reply. It should only return the requested range to its client. It should store the entire received response in its cache if that is consistent with its cache allocation policies. The refer request header field allows the client to specify for the servers benefit the address URI of the resource from which the request URI was obtained, the referrer. Although the header field is misspelled, the referrer request header allows a server to generate lists of backlinks to resources for interest logging, optimized caching, etc. It also allows obsolete or mistyped links to be traced for maintenance. The refer field must not be sent if the request URI was obtained from a source that does not have its own URI, such as input from the user keyboard. Refer equals refer. Absolute URI, relative URI. Example: refer http www.w3.org/hypertext/data sources/overview HTML. If the field value is a relative URI, it should be interpreted relative to the request URI. The URI must not include a fragment. See section 15.13 for security considerations. The retry after response header field can be used with a 503 service unavailable response to indicate how long the service is expected to be unavailable to the requesting client. This field may also be used with any 3xx redirection response to indicate the minimum time the user agent is asked wait before issuing the redirected request. The value of this field can be either an HTTP date or an integer number of seconds in decimal after the time of the response. Retry after equals retry after. HTTP date delta seconds. Two examples of its use are retry after Fry 31 Dec 1999 23:59 and 59 seconds. GMT retry after 120. In the latter example, the delay is 2 minutes. Server. The server response header field contains information about the software used by the origin server to handle the request. The field can contain multiple product tokens and comments identifying the server and any significant subproducts. The product tokens are listed in order of their significance for identifying the application. Server equals server. 1. Product comment. Example: server cern/3 libua/2.17. If the response is being forwarded through a proxy, the proxy application must not modify the server response header. Instead, it should include a via field as described in section 14.45. Note: revealing the specific software version of the server might allow the server machine to become more vulnerable to attacks against software that is known to contain security holes. Server implementors are encouraged to make this field a configurable option. The TE request header field indicates what extension transfer codings it is willing to accept in the response, and whether or not it is willing to accept trailer fields in a chunked transfer coding. Its value may consist of the keyword trailers and slash, or a comma-separated list of extension transfer coding names with optional except parameters. TE equals TE. Number T codings equals trailers. Transfer extension except params. The presence of the keyword trailers indicates that the client is willing to accept trailer fields in a chunked transfer coding as defined in section 3.61. This keyword is reserved for use with transfer coding values, even though it does not itself represent a transfer coding. Examples of its use are TE, deflate TE, TE, trailers, deflate Q equals 0.5. The TE header field only applies to the immediate connection. Therefore, the keyword must be supplied within a connection header field whenever TE is present in an HTTP/1.1 message. A server tests whether a transfer coding is acceptable according to a TE field using these rules. 1. The chunked transfer coding is always acceptable if the keyword trailers is listed. The client indicates that it is willing to accept trailer fields in the chunked response on behalf of itself and any downstream clients. The implication is that if given, the client is stating that either all downstream clients are willing to accept trailer fields in the forwarded response, or that it will attempt to buffer the response on behalf of downstream recipients. Note, HTTP/1.1 does not define any means to limit the size of a chunked response, such that a client can be assured of buffering the entire response. 2. If the transfer coding being tested is one of the transfer codings listed in the TE field, then it is acceptable unless it is accompanied by a Q value of 0 as defined in section 3.9. A Q value of 0 means not acceptable. 3. If multiple transfer codings are acceptable, then the acceptable transfer coding with the highest non-zero Q value is preferred. The chunked transfer coding always has a Q value of 1. If the TE field value is empty, or if no TE field is present, the only transfer coding is chunked. A message with no transfer coding is always acceptable. The trailer general field value indicates that the given set of header fields is present in the trailer of a message encoded with chunked transfer coding. Trailer equals trailer. One number field name and HTTP/1.1 message SHOULD include a trailer header field in a message using chunked transfer coding with a non-empty trailer. Doing so allows the recipient to know which header fields to expect in the trailer. If no trailer header field is present, the trailer should not include any header fields. See Section 3.61 for restrictions on the use of trailer fields in a chunked transfer coding. Message header fields listed in the trailer header field must not include the following header fields: transferring coding, content length trailer. The transferring coding general header field indicates what, if any, type of transformation has been applied to the message body. In order to safely transfer it between the sender and the recipient, this differs from the content coding in that the transfer coding is a property of the message, not of the entity. Transferring coding equals transferring coding. One number transfer codings are defined in Section 3.6. An example is transferring coding chunked if multiple encodings have been applied to an entity. The transfer codings must be listed in the order in which they were applied. Additional information about the encoding parameters may be provided by other entity header fields not defined by this specification. Many older HTTP/1 applications do not understand the transferring coding header. 14.42 Upgrade the upgrade general header allows the client to specify what additional communication protocols it supports and would like to use if the server finds it appropriate to switch protocols. The server must use the upgrade header field within a 101 switching protocols response to indicate which protocols are being switched. Upgrade equals upgrade. One number product, for example, upgrade HTTP/2, SHTTP/1.3, IRC/6.9, RTA/11. The upgrade header field is intended to provide a simple mechanism for transition from HTTP/1.1 to some other incompatible protocol. It does so by allowing the client to advertise its desire to use another protocol, such as a later version of HTTP with a higher major version number, even though the current request has been made using HTTP/1.1. This eases the difficult transition between incompatible protocols by allowing the client to initiate a request in the more commonly supported protocol indicating to the server that it would like to use a better protocol if available, where better is determined by the server, possibly according to the nature of the method and slash or resource being requested. The upgrade header field only applies to switching application layer protocols upon the existing transport layer connection. Upgrade cannot be used to insist on a protocol change. Its acceptance and use by the server is optional. The capabilities and nature of the application layer communication after the protocol change is entirely dependent upon the new protocol chosen. Although the first action after changing the protocol must be a response to the initial HTTP request containing the upgrade header field. The upgrade header field only applies to the immediate connection. Therefore, the upgrade keyword must be supplied within a connection header field section 14.1. Whenever upgrade is present in an HTTP/1.1 message, the upgrade header field cannot be used to indicate a switch to a protocol on a different connection. For that purpose, it is more appropriate to use a 301, 302, 303, or 305 redirection response. This specification only defines the protocol name HTTP for use by the family of hypertext transfer protocols as defined by the HTTP version rules of section 3.1 and future updates to this specification. Any token can be used as a protocol name. However, it will only be useful if both the client and server associate the name with the same protocol. 14.43 User Agent. The user agent request header field contains information about the user agent originating the request. This is for statistical purposes, the tracing of protocol violations, and automated recognition of user agents for the sake of tailoring responses to avoid particular user agent limitations. User agents should include this field with requests. The field can contain multiple product tokens. Section 3.8 and comments identifying the agent and any subproducts which form a significant part of the user agent. By convention, the product tokens are listed in order of their significance for identifying the application. User agent equals user agent 1 product comment example user agent cernline mode /2.15 libua /2.17b3 The very field value indicates the set of request header fields that fully determines, while the response is fresh, whether a cache is permitted to use the response to reply to a subsequent request without revalidation for uncacheable or stale responses. The very field value advises the user agent about the criteria that were used to select the representation. A very field value of implies that a cache cannot determine from the request headers of a subsequent request whether this response is the appropriate representation. See section 13.6 for use of the very header field by caches. Very equals very. One number field name, an HTTP/1.1 server SHOULD include a very header field with any cacheable response that is subject to server-driven negotiation. Doing so allows a cache to properly interpret future requests on that resource and informs the user agent about the presence of negotiation. A server may include a very header field with a non-cacheable response that is subject to server-driven negotiation. Since this might provide the user agent with useful information about the dimensions over which the response varies at the time of the response. A very field value consisting of a list of field names signals that the representation selected for the response is based on a selection algorithm which considers only the listed request header field values in selecting the most appropriate representation. A cache may assume that the same selection will be made for future requests with the same values for the listed field names for the duration of time for which the response is fresh. The field names given are not limited to the set of standard request header fields defined by this specification. Field names are case insensitive. A very field value of signals that unspecified parameters not limited to the request headers, e.g., the network address of the client, play a role in the selection of the response representation. The value must not be generated by a proxy server. It may only be generated by an origin server. The via general header field must be used by gateways and proxies to indicate the intermediate protocols and recipients between the user agent and the server on requests, and between the origin server and the client on responses. It is analogous to the received field of RFC 822.9 and is intended to be used for tracking message forwards, avoiding request loops, and identifying the protocol capabilities of all senders along the request/response chain. Via equals via. One number received protocol received by comment. Received protocol equals protocol name slash protocol version. Protocol name equals token. Protocol version equals token received by equals host. Port pseudonym equals token. The received protocol indicates the protocol version of the message received by the server or client along each segment of the request/response chain. The received protocol version is appended to the via field value when the message is forwarded, so that information about the protocol capabilities of upstream applications remains visible to all recipients. The protocol name is optional if and only if it would be HTTP. The received by field is normally the host and optional port number of a recipient server or client that subsequently forwarded the message. However, if the real host is considered to be sensitive information, it may be replaced by a pseudonym. If the port is not given, it may be assumed to be the default port of the received protocol. Multiple via field values represents each proxy or gateway that has forwarded the message. Each recipient must append its information such that the end result is ordered according to the sequence of forwarding applications. Comments may be used in the via header field to identify the software of the recipient proxy or gateway, analogous to the user agent and server header fields. However, all comments in the via field are optional and may be removed by any recipient prior to forwarding the message. A request message could be sent from an HTTP/one user agent to an internal proxy codenamed Fred, which uses HTTP/1.1 to forward the request to a public proxy at nowhere.com, which completes the request by forwarding it to the origin server at www.ikes.usa.edu. The request received by www.ikes.usa.edu would then have the following via header field: via 1 Fred 1.1 nowhere.com Apache/1.1. Proxies and gateways used as a portal through a network firewall should not, by default, forward the names and ports of hosts within the firewall region. This information should only be propagated if explicitly enabled. If not enabled, the received by host of any host behind the firewall should be replaced by an appropriate pseudonym for that host. For organizations that have strong privacy requirements for hiding internal structures, a proxy may combine an ordered subsequence of VIA header field entries with identical received protocol values into a single such entry. For example, VIA 1 Ricky, 1.1 Ethel, 1.1 Fred, 1 Lucy could be collapsed to VIA 1 Ricky, 1.1 Mertz, 1 Lucy. Applications should not combine multiple entries unless they are all under the same organizational control, and the hosts have already been replaced by pseudonyms. Applications must not combine entries which have different received protocol values. 14.46 Warning. The warning general header field is used to carry additional information about the status or transformation of a message which might not be reflected in the message. This information is typically used to warn about a possible lack of semantic transparency from caching operations or transformations applied to the entity body of the message. Warning headers are sent with responses using warning equals warning, one number warning value, warning value equals warn code SB, warn agent SB warn text, SB warn date, warn code equals 3-digit, warn agent equals host, port pseudonym, the name or pseudonym of the server adding the warning header for use in debugging. Warn text equals quoted string. Warn date equals HTTP date. A response may carry more than one warning header. The warn text should be in a natural language and character set that is most likely to be intelligible to the human user receiving the response. This decision may be based on any available knowledge, such as the location of the cache or user, the accept language field in a request, the content language field in a response, etc. The default language is English, and the default character set is ominous 8,859-1. If a character set other than is ominous 8,859-1 is used, it must be encoded in the warn text using the method described in RFC 2047-14. Warning headers can in general be applied to any message. However, some specific warn codes are specific to caches. and can only be applied to response messages. New warning headers should be added after any existing warning headers. A cache must not delete any warning header that it received with a message. However, if a cache successfully validates a cache entry, it should remove any warning headers previously attached to that entry, except as specified for specific warning codes. It must then add any warning headers received in the validating response. In other words, warning headers are those that would be attached to the most recent relevant response. When multiple warning headers are attached to a response, the user agent ought to inform the user of as many of them as possible, in the order that they appear in the response. If it is not possible to inform the user of all of the warnings, the user agent should follow these heuristics. Warnings that appear early in the response take priority over those appearing later in the response. Warnings in the user's preferred character set take priority over warnings in other character sets, but with identical warn codes and warn agents. Systems that generate multiple warning headers should order them with this user agent behavior in mind. Requirements for the behavior of caches with respect to warnings are stated in section 13.12. This is a list of the currently defined warn codes, each with a recommended warn text in English and a description of its meaning. 110 response is stale must be included whenever the returned response is stale. 111 revalidation failed must be included if a cache returns a stale response because an attempt to revalidate the response failed due to an inability to reach the server. 112 disconnected operation should be included if the cache is intentionally disconnected from the rest of the network for a period of time. 113 heuristic expiration must be included if the cache heuristically chose a freshness lifetime greater than 24 hours and the response's age is greater than 24 hours. 199 miscellaneous warning. The warning text may include arbitrary information to be presented to a human user or logged. A system receiving this warning must not take any automated action besides presenting the warning to the user. 214 transformation applied must be added by an intermediate cache or proxy. If it applies any transformation changing the content coding as specified in the content encoding header or media type, as specified in the content type header of the response, or the entity body of the response, unless this warning code already appears in the response. 299 miscellaneous persistent warning. The warning text may include arbitrary information to be presented to a human user or logged. A system receiving this warning must not take any automated action if an implementation sends a message with one or more warning headers whose version is HTTP/1 or lower. Then the sender must include in each warning value a warn date that matches the date in the response. If an implementation receives a message with a warning value that includes a warn date, and that warn date is different from the date value in the response, then that warning value must be deleted from the message before storing, forwarding, or using it. This prevents bad consequences of naive caching of warning header fields. If all of the warning values are deleted for this reason, the warning header must be deleted as well. 14.47 www authenticate. The www authenticate response header field must be included in 401 unauthorized response messages. The field value consists of at least one challenge that indicates the authentication schemes and parameters applicable to the request URI. www authenticate equals www authenticate. 1 number challenge. The HTTP access authentication process is described in HTTP authentication, basic and digest access authentication. 43. User agents are advised to take special care in parsing the www authenticate field value, as it might contain more than one challenge, or if more than one www authenticate header field is provided. The contents of a challenge itself can contain a comma-separated list of authentication parameters. 15 security considerations. This section is meant to inform application developers, information providers, and users of the security limitations in HTTP/1.1 as described by this document. The discussion does not include definitive solutions to the problems revealed, though it does make some suggestions for reducing security risks. 15.1 Personal information. HTTP clients are often privy to large amounts of personal information, e.g. the user's name, location, mail address, passwords, encryption keys, etc., and should be very careful to prevent unintentional leakage of this information via the HTTP protocol to other sources. We very strongly recommend that a convenient interface be provided for the user to control dissemination of such information, and that designers and implementors be particularly careful in this area. History shows that errors in this area often create serious security and slash or privacy problems, and generate highly adverse publicity for the implementor's company. 15.11 Abuse of server log information. A server has the capability to store personal data related to a user's requests that could identify their reading habits or interests. This type of information is considered highly confidential, and its management may be regulated by laws in some countries. Users providing data through HTTP are responsible for ensuring such material is not disseminated without the consent of any identifiable individuals from the published results. 15.12 Transfer of sensitive information. Just like other data transfer protocols, HTTP does not control the content of transferred data, and there's no way to determine in advance the sensitivity level of specific information within a request context. Therefore, applications should offer as much control over this information as possible to those providing it. 4. Header fields are especially noteworthy. Server, via, referrer, and from, revealing the server software version, could make the server machine more vulnerable to attacks targeting known security flaws in that software. Implementors should configure the server header field as an option. Proxies acting as a gateway through a network firewall should take special precautions regarding transferred header information that identifies hosts behind the firewall. They should remove or replace with sanitized versions any via fields generated behind the firewall. The referrer header can be used to track reading patterns and establish reverse links, which could be very useful, but its power can be misused if user details are not separated from the information contained in it. Even when personal data is removed, the referrer header might indicate a private document's URI whose publication would be inappropriate. Information sent in the from field may conflict with a user's privacy interests or their site's security policy, and thus should not be transmitted without allowing users to disable, enable, and modify its contents. Users must have the ability to set the contents of this field within Preferences or Application Defaults configurations. We recommend, but do not require, providing a toggle interface for users to enable or disable sending from and referrer information. The User Agent section 14.43 or Server section 14.38. Header fields can sometimes be used to determine that specific clients or servers have particular security holes which might be exploited. Unfortunately, this same information is often used for other valuable purposes, currently not better addressed by HTTP. 15.13 Encoding sensitive information in URIs. Since the source of a link might contain private information or reveal an otherwise private information source, it is strongly advised that users have control over sending the referrer field. For instance, a browser client could include a toggle switch for anonymous browsing, which would enable or disable sending the referrer and from information. Clients should not include a referrer header in non-secure HTTP requests if the referring page was transferred with a secure protocol. Authors of services using HTTP should avoid using GET-based forms for submitting sensitive data, as this will encode it in the request URI. Many existing servers, proxies, and user agents may log request URIs where they might be accessible to third parties. Servers can use post-based form submission instead. 15.14 Privacy issues connected to accept headers. Accept headers can reveal information about users to all accessed servers. The accept language header in particular can expose private details because the understanding of specific languages is often HTTP origin server implementations should carefully restrict documents returned by HTTP requests to only those intended by server administrators. If an HTTP server translates HTTP URIs directly into file system calls, special care must be taken not to serve files not meant for delivery to HTTP clients. For example, on systems using as a path component to indicate a directory level above the current one. Such constructs in the request URI should be disallowed if they would otherwise allow access to resources outside those intended. Similarly, files intended only for internal reference by the server, like access control files, configuration files, and script code, must be protected from inappropriate retrieval, as they might contain sensitive information. Experience has shown that minor bugs in such HTTP server implementations can turn into security risks. Clients relying on HTTP place heavy dependence on the domain name service and are thus generally vulnerable to security attacks based on deliberate misassociation of IP addresses and DNS names. Clients should be cautious in assuming the continuing validity of an IP /DNS name association. HTTP clients should rely on their name resolver for confirmation of an IP /DNS name association rather than caching the result of previous host name lookups. Many platforms can cache host name lookups locally when appropriate and should be configured to do so. However, these lookups should only be cached if the TTL information reported by the name server makes it likely that the cached information will remain useful. If HTTP clients cache results of host name lookups in order to achieve performance improvements, they must observe the TTL information reported by DNS. Failing to do so could lead to spoofing when a previously accessed server's IP address changes. Given the expected increase in network renumbering 24, observing this rule reduces potential security vulnerabilities. This requirement also improves load balancing behavior for clients using replicated servers with the same DNS name and decreases the likelihood of users experiencing failure accessing sites that use such a strategy. If a single server supports multiple organizations that do not trust one another, then it must check the values of location and content location headers in responses generated under control of said organizations to make sure that they do not attempt to invalidate resources over which they have no authority. 15.5 Content Disposition Issues RFC 18.6, from which the often implemented content disposition header in HTTP is derived, has a number of very serious security considerations. Content disposition is not part of the HTTP standard, but since it is widely implemented we are documenting its use and risks for implementors. See RFC 2183, which updates RFC 18.6 for details. 15.6 Authentication credentials and idle clients. Existing HTTP clients and user agents typically retain authentication information indefinitely. HTTP/1.1 does not provide a method for a server to direct clients to discard these cached credentials. This is a significant defect that requires further extensions to HTTP. Circumstances under which credential caching can interfere with the application's security model include, but are not limited to, clients which have been idle for an extended period, following which the server might wish to cause the client to reprompt the user for credentials, applications which include a session termination indication, such as a logout or commit button on a page, after which the server side of the application knows that there is no further reason for the client to retain the credentials. This is currently under separate study. There are a number of workarounds to parts of this problem, and we encourage the use of password protection in screensavers, idle timeouts, and other methods which mitigate the security problems inherent in this problem. In particular, user agents which cache credentials are encouraged to provide a readily accessible mechanism for discarding cached credentials under user control. 15.7 Proxies and caching by their very nature. HTTP proxies are men in the middle and represent an opportunity for man-in-the-middle attacks. Compromise of the systems on which the proxies run can result in serious security and privacy problems. Proxies have access to security-related information, personal information about individual users and organizations, and proprietary information belonging to users and content providers. A compromised proxy, or a proxy implemented or configured without regard to security and privacy considerations, might be used in the commission of a wide range of potential attacks. Proxy operators should protect the systems on which proxies run as they would protect any system that contains or transports sensitive information. In particular, log information gathered at proxies often contains highly sensitive personal information, and slash or information about organizations. Log information should be carefully guarded, and appropriate guidelines for for use, developed, and followed. Caching proxies provide additional potential vulnerabilities since the contents of the cache represent an attractive target for malicious exploitation. Because cache contents persist after an HTTP request is complete, an attack on the cache can reveal information long after a user believes that the information has been removed from the network. Therefore, cache contents should be protected as sensitive information. Proxy implementors should consider the privacy and security implications of their design and coding decisions, and of the configuration options they provide to proxy operators, especially the default configuration. Users of a proxy need to be aware that they are no trustworthier than the people who run the proxy. HTTP itself cannot solve this problem. The judicious use of cryptography, when appropriate, may suffice to protect against a broad range of security and privacy attacks. Such cryptography is beyond the scope of the HTTP/1.1 specification. Denial of service attacks on proxies exist. They are hard to defend against. Research continues. Beware.